Jagannavan sir.
Good evening, you all.
Good evening, sir.
మేడం
Sir.
మేడం సార్ ఒక 2 minutes జాయిన్ అవుతున్నారు.
Okay, okay, sir.
సార్ కనిపిస్తున్నారు సార్.
ఓకే
ఓకే సార్.
We request all the participants to kindly switch off your mic. Jagannath sir.
మేడం చెప్పండి.
Sir, shall we start?
సార్ జాయిన్ అయ్యారా మేడం? మేడం ప్రిన్సిపల్ సార్ జాయిన్ అయ్యారు.
అదే సార్ చూస్తున్నాను, నాకు ఐ కుడ్ నాట్ ఏబుల్ టు గెట్ ఇట్.
ఒకసారి మళ్ళీ ఫోన్ చేయండి మేడం. నేను చెప్పాను, ఇప్పుడే చెప్పాను.
సరే. Naveen sir, I think sir has joined.
Yeah, good evening.
Good evening, sir.
Jagannath. Good evening.
Yes.
Good evening.
Shall
Good
I
evening,
start,
sir.
sir?
Yes, yes, yes. Please go ahead. Please
Good
go ahead.
evening, sir.
Good evening. Good evening.
Chief guest of today's inaugural session, Dr. Rajendra Dagla sir, Director, Scientist F, RCI DRDO Hyderabad, respected Principal Dr. CLV RSV Prasad sir, beloved HOD of EC Department Dr. V. Jagannath sir, FTP Co-Coordinator Dr. Vasudeva Bevra sir, Associate Deans, Academic Heads, Faculty Members and Participants, a very good evening to one and all. It is our honor and privilege to welcome you all to the AICT-sponsored 6-day online faculty development program on VLSI design innovations for defense applications, scheduled from 9th December to 14th December 2024. We are thrilled to have you join us for this inaugural ceremony for this online FDP. As we gather here today, we recognize the critical role that VLSI design plays in shaping the future of defense technology. The rapid advancements in this field have opened up new avenues for innovation and collaboration. The aim of this FDP is to revolutionize defense system through cutting-edge VLSI design innovation is a pivotal for enhancing military capabilities. Advanced VLSI technologies enable the integration of complex functionalities into compact, high-performance chips, allowing for a real-time data processing and improved system reliability. Innovations such as a low power consumption and high speed processing empower the defense applications like surveillance, communication, and weaponry. So these advancements not only improve existing defense mechanism but also create opportunities for developing next generation solutions, ensuring a strategic superiority in an increasingly complex global environment. This faculty development program also aims to provide a platform for academics, researchers, and industry experts to share their knowledge, experiences, and best practices in VLSI design innovation for defense applications. Over the next 6 days, we have curated technical sessions handling by our various resource persons. Will delve into cutting edge topics like VLSA applications in defense technology, AI algorithms to VLSA architectures mapping, ASIC and FPGA implementation in advanced VLSI, analog and mixed signal circuit design with emerging CMOS technologies, power analysis in VLSI. So we believe that this program will not only enhance your practical technical expertise, but also foster a meaningful connections and collaborations among participants. Before we begin, I would like to express our sincere gratitude to AICTE for sanctioning and sponsoring this 6-day online FDP. Also, I'd like to express our sincere gratitude to our management Your support has been instrumental in making this program a reality. Before concluding my address, I am happy to inform you that 151 participants have registered from various parts of our country. I hope the 6 days online FDP will be an eye opening for all the participants. Once again, I welcome you all for this faculty development program. We look forward to your active participation, engaging discussions, and valuable contributions. So let us work together to harness the power of VLSI design innovation for defense applications and create a brighter future for our nation. Thank you. Now I request our beloved HOD EC, Dr. Jagannathan sir, to address the participants.
Thank you, madam. Good evening, Principal sir. Today's chief guest, Dr. Rajendra sir from DRDO. He's the director there, Hyderabad, and all academic deans, heads of the departments, faculty participants, and coordinators. A warm welcome to 6-day faculty development program on VLSI design innovations for defense applications. Around 150 participants participated throughout the country. I congratulate the coordinators. Within a short span of time, we have communicated to the people. The main objective of the FDP is to emphasize the importance of VLSI in the defense applications. And it also majorly focuses on energy efficiency and system reliability in VLSI with low power and high-speed VLSI design applications, data processing. It also ensures the current research trends in AI-enabled VLSI chip designs for autonomous defense systems. In this 6 days FDP, the resource persons are from the industry, DRDO Hyderabad, Moss Chip Technologies Hyderabad, Samsung Semiconductors India Research Bangalore, Entrepreneur Technologies Bangalore, Digicom Semiconductors Bangalore, Western Digital Semiconductors Bangalore. And the resource persons we are taken from the institutions are IISCR Bhopal, JNTU Kakinada, TUS University Bangalore, Experia Netherlands, and Tan University Vietnam. We thank all the resource persons for accepting the request in spite of the busy schedule. We once again thank our director, DRDO director Rajendra sir, for accepting the request. And once again, we thank the AST, GMRT management and coordinators, Dr. Sivasankari madam and co-coordinator Vasudev Rao for continuous support for organizing this FDP. Thank you all. Over to Sivasankari madam.
Thank you, sir. Now I request our energetic principal, Dr. CLV RSV Prasad sir, to address the participants.
Thank you, Dr. Shivshankari. Today's chief guest, Dr. Rajendra, from Director RCA DRDO Hyderabad. Other participants who are all there present, I think around 96 participants are there as of now online. And all the advisory board members, and then a convener, co-convener, and organizing committee. A very good evening to all of you. At the outset, I would like to compliment and congratulate the convener and co-convener for putting on the continuous efforts in designing and formulating the FDP. And finally, they are successful in getting funded by this AACT under AACT Training and Learning Academies sponsorship. And I'm very sure that the objectives that are laid down for this FDP are very clear and very focused. And all the resource persons who have readily accepted, like no, our today's chief guest, Dr. Rajendra and Dr. Anand, and Dr. Geetanath, and Dr. Bahubalendruni, Dr. Balaji, Dr. Manikanta, Charan, Dr. Sudhindra, and then Dr. Nagaraju, Nag Subramaniam, Dr. L. Govind. I'd like to thank one and all by name for accepting to be the resource persons for this in the 5 days time program. And also I would like to request all the participants to take all the sessions very seriously, attend the program continuously, and so that they have a key takeaways from out of the 6 days workshop. And the purpose of this workshop will be served only if these key takeaways are there carried to the respective stakeholders in their respective institutions, that is their students. And I'm sure that the takeaway from this will be very valuable, and this will be a very good learning exercise for the students in the respective institutions. So I again request all the participants to be very focused, not to miss any session, and to be regular and in attending all the sessions. And finally, I would like to again compliment all the organizing team here from GMR Institute of Technology for planning this and organizing this. So thank you very much, sir. And also I'd like to thank today's chief guest, Dr. Rajendra, once again for accepting. Thank you very much, sir, Rajendra Garu, for accepting for the resource person and the chief guest. So all the best. Good luck.
Yeah, thank you. It's my pleasure to come in front of you all people.
Thank you, sir. Thank you very much. Thank you very much.
Thank you, sir.
Over to, yeah.
Thank you, sir. Now I call upon Dr. T. Geetama, Associate Professor of EC Department, to introduce the guest.
Thank you, ma'am. Good evening, sir. Good evening to all participants. It's my pleasure to introduce today's chief guest, Dr. Rajendra Dagula. Dr. Rajendra received BTech degree in Electronics and Communication Engineering from Regional Engineering College, Warangal. MTech degree in Electronic Design Technology from Indian Institute of Science, Bangalore. And PhD in Microelectronics and VLSI from Indian Institute of Technology, Hyderabad. He has joined Defense Research and Development Organization in the year 2002 as a scientist and has been working in the design and development missile-borne miniaturized radar system. He is project director for design and development of radar for active protection system. Dr. Rajendra is a senior member of IEEE. His research areas include radar system design, radar signal and data processing, HDL IP development and validation for RF sensors and communication systems, RF circuits, microwave and RF system design, and slotted waveguide array antenna design. He has 20 years of experience with numerous achievements and recognitions. He is recipient of Agni Award for Excellence in Self-Reliance for outstanding contributions in the design and development of indigenous anti-ballistic missile defense system for the country, and DRDO Technology Development Award for distinctive contributions in design and development missile-borne miniaturized radar system. Thank you, sir. Thank you so much. Now I hand over this session to the Dr. Rajendra.
So good evening all.
Good evening, sir.
Good evening, sir.
Yeah, good evening, good evening. Yes, I'm sharing my presentation. Is my presentation visible?
Yeah, it's clear. You need to get into the presentation mode. Yes. Yeah.
Visible, sir.
Yeah, so good evening all. Today's topic of discussion is VLSI design innovations in defense technology. So major things I'll focus on the defense technologies, how we are going to use the VLSI technologies. So in realizing these defense equipment so that they will be working at precise and low power operations and all. So the areas of VLSI technology is classified into, so based on the functionality, it is classified, and based on technology and based on applications. So based on functionality, there are analog ICs. So we can see like amplifiers, sensor and regulators, and digital ICs, logic gates, microprocessor, memory, and mixed signal ICs so like ADCs and ESIs. These will be having analog part as well as a digital part. And we'll be having like photonic ICs like MEMS and photonic ICs. So IC design areas are digital IC design, so analog IC design, RF IC design, optical IC design, and microelectronic, microelectromechanical IC design. So each of the area is a distinctive area. So expert in one area may not be like expert in another area. So these are different areas altogether. So when we integrate all these IC design activities into a single chip, so this will work as a system on chip. So based on the application, now general purpose ICs are there, like op-amps and logic ICs and ASICs. So application specific integrated circuits. So these are specific to like smartphone IC and some television chips or refrigerator or automotive chips. So these are specific to that application only. So in one application, ASIC cannot be used in for another application. And FPGAs, these are reconfigurable ICs. So this is a most important technology for defense applications. So 80% of the applications are realized by using FPGAs rather than the application-specific integrated circuits. The basic reason is, so these FPGAs can be programmed in the field. So we can program in the field based on the requirement or application. So whereas the ASICs, once the application is freezed by using the FPGA technology, and we have a huge number of chips to be produced, then only we'll go for the SoC or ASIC application. But whereas the defense technology, these numbers may not be like as commercial IC requirements. So that's why most of the things are realized by using the FPGA technology only. And this is a single architecture of FPGA suitable for numerous applications, whether it can be radars or communication, or it can be like control, whatever it may be. So a single FPGA architecture we can program for any kind of application. So this is the advantage of FPGAs. And SOCs are used like where there are huge number of ICs to be produced, like millions of ICs to be produced. So these are like costly solutions. Initial setup costs are required. So after that, like production cost will be very less. So like when there are a huge number of ICs to be produced, then the system on chip applications are used. So this will be having all the things on a single die. So whether it is a CPU, memory, or IOS, or it can be analog part. So all these things are integrated onto a single transistor, single die. So now actually like when we talk about VLSI, so we are integrating like billions of transistors on a single die. So I actually it should be wrongly nomenclatured as VLSI, it should be nomenclatured as ULSI. So when we are studying from like 2000 onwards, it was the same word, it was continuing till now. So, but now from there, from that time onwards to now, there is a lot of increased improvement in the IC design technology. So in the tools as well as the fabrication technology, there is a lot of improvements. So now the technology to be like removed, but VLSI became famous and it is still continuing the same word. So now based on the technology, like so based on the bipolar ICs, we are using guys gallium nitride, gallium arsenide. So these are used for high power applications, for RF applications. These technologies are used. So like MOS ICs based on the like CMOS or NMOS, PMOS. Some applications need analog IC designs, NMOS and PMOS wherever we need. And by CMOS IC is like a combination of bipolar as well as the CMOS technology we use. So these are BJTs as well as the CMOS. So by CMOS applications basically are very famous for in the development design of like this RFICs for communications as well as phased radars. So these by CMOS ICs are used. So this is the very classification of IC design technology. So like for each of the technology, there will be one process node and there will be so models PDKs given by the fab. So based on the PDKs, we have to customize our device and we have to do like a simulation studies of that particular device, and we have to configure the circuitry around that devices, and we have to see whether the functionality is meeting our requirements or not, can be verified by using the advanced development tools. So with all this, we can we can initially simulate the IC and we can give it for to the fab so that the IC will be fabricated. So if you see the VLSI IC design flow, so first we'll arrive the system specifications. So what are the complete system specifications for to meet our mission requirements? So we'll formalize all the requirements initially. So the design reviews will be conducted by the expert teams. So they will be reviewing the design, and finally the design specifications are freezed. So from that we have to identify the architecture, like so what should be architecture, like automatic logic unit, or so how many IOs it should have, how much memory it should have. So what is the analog part? In analog part, what are the circuits, whether that are band gap references or so comparators, what should be there. So all that and op amps. So in RF design, like whether it is a mixer or power amplifier or LNA, so all this architecture, everything will be finalized by the design team. So after thorough architecture finalization, so individual parts will be given to the respective design teams. So the design teams, what they will do is they will, from this architecture, so they will develop the circuit or functional logic design stage. So they will develop the functional blocks. They will divide this architecture into sub-modules and they will realize the functionality. And this functionality can be like, it can be HDL coded or it can be like model-based design. So later, for analog design, it will be circuit-based designs, and for so RF also circuit-based designs. So all these things will be simulated by respective design teams. Okay, from there, like circuit design will be performed. So and time like functional analysis will be done. So after this completion of this circuit design, synthesis of the circuit for the digital part, like from architectural to like circuit level, from circuit level to transistor level synthesis will be done by the these teams. And from there, the circuits will be physical design will be done. So the circuits will be put onto the layout part. So then after that, we'll do physical verification whether it is meeting all the design rule constraints, whether the transistor sizes and their spacings, all those things are met or not. The physical verification will be done. Then post processing of the layout generation of the required files will be done by using the layout post processing. Then the after generation of the layout files will be sent to the fab. So generally it will take like 6 months cycle time. So the IC will be fabricated by using the layout post processing. The fabricated die will be received by the design team, and so they will be packaging. After packaging, we need a lot of test equipment, like bonding of the IC, as well as after that we'll need some network analyzers and spectrum analyzers and logic analyzers. With all those things, we'll test the IC, thoroughly tested. So after testing the IC, what we'll do is that IC we have to put in package in a PCB. So after that, we have to package in the PCB. So after the PCB fabrication, PCB PCB mounting onto the assembly onto the PCB, then the system will be enclosed in a enclosure, and the system will be tested. So this is the flow for the from VLSI IC design to the complete system design flow will be like this. So the importance of VLSI in defense is, in almost all defense equipment, our electronics is an integral and essential part of all those systems. So if you take any defense equipment, there will be compulsory electronic systems are integral part. So all electronic systems are made up of integrated circuits. ICs are must. So whether it is a control system, communication system, whatever it may be. So ICs are there. So that IC need to be designed by innovative teams. So they have to follow like the latest current trends. What is the latest node technology node they have to adapt, and they have to learn the tools, and they have to design the IC for that application. And defense system need real-time processing of data. So it's a defense system, you have to process real-time. Offline data processing is not acceptable. So real-time, you have to process that data, and you have to take real-time decisions, and you have to, whether it can be firing off fire control system, or you have to stop the incoming threat. So neutralize the incoming threat. All those things we need real-time processing. So for that we need higher processing capability. So that is possible only with the VLSI technology. So without VLSI technology, it's difficult to process the incoming sensor data. So real processing capability is possible with VLSI only. And VLSI enables security encryption for secure communication. So in a battlefield, so enemy should not intercept our information. So for that, security encryption plays a major role. So for that, we need to have so longer word length keys, so that the enemy cannot decrypt in the given time frame. So for that we need VLSI technology. So and it is essential for advancement of our defense systems. So we have to deliver high power, high performance, low weight, volume, and low power systems. It's a continuous evolvement technology. So R&D, there are no limits for R&D in the VLSI. So now in India, so there is a lot of requirement for defense equipment. So in one way, we can say we are at the preliminary stage of development of these systems. Most of the ICs that today we are using are imported, like commercial ICs we are adopting for the these applications. But whereas for a FPGA-based systems, where you are developing our own our system specifications, we are our own systems we are developing, and we are realizing those systems, and we are that are deployed in the field, and they are working successfully for years together. And innovation in VLSI is the key driving force in modernizing our defense systems. So to modernize our defense systems, so VLSI in innovation technology is important, and we have to develop the teams, and we have to bring up the youngsters, the spirit of development of these systems, so that the people will be encouraged, so that they will realize these defense system, and it will be beneficial for our country. And most of the defense systems nowadays, some of the not now. So earlier we used to import most of the systems. Now with the Make in India concept, we are making most of the systems in India only. So that's a good initiative by our government, so that we are our country is benefited by the indigenous development of defense systems. So our defense systems are this is a chart shows our how the defense systems are classified. So generally, major classifications are our aero systems, aeronautical systems like fighter aircrafts, UAVs for surveillance, pilotless targeted aircrafts, and UAVs for as a weapon. So and airborne early warning radars. These are all comes under aero systems. And for a fighter crafts, if you see, there will be a lot of equipment. So a lot of avionic systems are there, are all electronic systems. So all those things needs a big teams to develop each of the subsystem ICs, and finalizing and realizing the system. So naval system, if you take a naval system, so there are warships are there, submarines are there, anti-ship torpedoes, depth charges, point defense systems. So like this point defense system, like to defend the ship from incoming threats. So for each of the warship, how much big it is and how much electronics it will contain. So for all this development of these things, so you assume like how much manpower is required. So these are all complicated systems. So now actually most of the systems, like most of the ICs that are used in these systems are imported ICs, but we have to indigenously we have to develop, and some of the systems we are developing the with our available limited manpower, we are developing the required systems indigenously. And next is a ground combat systems like armored fighting vehicles that are tanks. So Arjun, MBT, all those tanks are comes under this ground combat systems. And missiles and strategic systems. If you take missiles, there are so air-to-air missiles, so air-to-surface missiles, surface-to-air surface missiles, and ballistic blast missiles and cruise missiles. And another class is surface-to-air missiles. So these are a different class of missiles, and each will be having multiple number of missiles in each of these classes. So these are only 4 classes at the top level, but now we are developing more than like 50, 60 types of missiles in India. So all these missiles will fall under these 4 categories. And depending on the mission requirements or range requirements or reaction time requirements, we are developing each of the missile systems. And armament and artillery. This is a very important area. So like for ammunition of 120 mm or 125, 150 mm ammunition, these ammunitions are developed produced in numbers, very large numbers. These ammunition are produced, and they are stored in the they are stored. And to fire these things, we need artillery guns. So these are to be produced, and this ammunition needs a lot of electronics. So it will be having for guidance system will be there in the ammunition, as for giving the firing pulse to the warhead. There will be like time-based firing pulse or proximity-based fuses. So all those things will be incorporated into the ammunition. And fuses. So there are different types of fuses. The time-based fuses or proximity-based fuses or altitude-based fuses. There are different types of fuses. So the electronics are ICs that we need, and rocket systems. So these rockets, nowadays we have guided rockets are available. So for 20 kilometers, 40 kilometer targets to neutralize. So we are using these rocket systems. And if you see the electronic systems, so like these are electronic warfare systems. So we have to so understand, like we need electronic support images and electronic. We have to this objective of electronic warfare system is we have to enable our we have to use the electromagnetic spectrum and disable the enemy to use the electromagnetic spectrum. That is the objective of the electronic warfare system. For that, electronic support images, so electronic countermeasures, electronic countermeasures, so that the enemy cannot use the electromagnetic spectrum. And if even the enemy is suppressing us from using the electromagnetic spectrum, we have to use the electromagnetic spectrum by using the electronic countermeasures. So these are the warfare tactics we have to employ. So in electronic
Sir Rajendra sir, you are muted, sir. Please unmute yourself. Okay, sir. You continue. Sir.
that muting happened now only, or is it happened now only, or
Just now, sir. Just now. You can
just now?
continue,
Okay.
sir. Okay, you can continue.
Yes. So whenever just it is getting muted, you just let us know. It's automatically happening. I don't know why. So
Definitely, sir.
now after this electronic system, there are radar systems. So these radar systems are all of So there are a huge number of radars, types of radar system. It can be like ground radars, it can be like fighter jet radars, or it can be a radar for tracking drones. So different application needs different radar systems, and the design and development of each of the radar system is unique. So one type of radar, if you designed, it cannot be used for other applications. So depending on the application, the design will change. So that's why we need a lot of manpower and all for the relation of these radar systems. And the communication systems, all of these are very essential for in order to communicate between our troops and sending audio as well as video data among the troops. And electro-optical systems, these are
Sir, again muted, sir. Sir, again muted.
something. Yeah, moderator has to do something. I'm not muting, I'm presenting, but I don't know why it is automatically getting muted. So then next is the infrared sensors are there.
It's muted, sir.
Kalyan, sir.
So moderator, yeah. So was there somebody has to do something? I don't know why it is getting muted every time. Huh?
Sir, we are checking, sir.
Yeah.
Yes, sir.
Yeah. So for space systems, like for defense, there are specific satellites are available. So this will give situational awareness, like what are the threats from the enemies, and all that will be sensed by these satellites. And the communication, like they are launching any missiles, so that will be sensed by these satellites, and it will alert our defense forces to launch our counter measures. And secure communication systems are possible with the space systems, and surveillance and reconnaissance. Yeah, so for navigation and positioning, we'll use. I'm audible now?
Yes, sir.
Yes, sir, you are audible.
Sir.
Yes, sir. Audible,
Yes,
sir.
audible.
Yeah. So for navigation and positioning, your GPS, all of you know, without GPS nowadays we cannot navigate. So it's essential integral part of our daily system. But these
Sir, again muted, sir.
so this presentation, just I'll that muting every time I'll keep. Okay. So we need very high accuracy for defense applications. For that, we need defense satellites so that they enable us for navigating and positioning of our missiles. And early warning systems are essential in order to give clear information about the enemy radar threats. So ELINT also they will give the electronics intelligence from the space. And another area is microelectronics and server systems. So these will enable like advanced technologies like solid-state physics research, as well as quantum technologies, artificial intelligence, and autonomous systems. So these are the areas these streams will work. So these are the broad areas where different areas of the defense equipment will work. So this is a broad classification. So if you look at any typical VLSI system, so generally there will be there are some RF circuitry will be there. So for the generation of any waveform, whether it can be like a communication system, or it can be a radar system, or it can be like a sensor system, some sensor RF sensor. So it will be having typically one sensor that will generate a waveform, and the waveform will be transmitted by using the transmitting antenna, and it will be received by another LNA. It can be like any frequency band, like from starting from megahertz, so UHF or VHF to up to terahertz frequencies, up to
Sir, your voice is muted, sir.
whereas intelligence is there in the so I'm keeping side by side. So I'll present like this. Is my screen is visible for you?
Yes, sir, it is visible.
Yes, sir. Yes, sir. It is visible.
So I'll go ahead like this, so that this muting unmute I'll come to know whether when it is getting unmuted, when it is getting muted. So this is the typical system, so which is having all the things. Now in this system only, based on our requirements, we have to customize each of the blocks. So like RF requirements are there depending on the frequency band, or depending on the dynamic range requirements, or depending on the transmitted power. So based on these requirements, we have to customly develop these amplifiers or synthesizers, whatever it is. So we have to customize depending on our requirement. Depending on the LNA also, then analog to digital converters. So it will be having specifications like what is the sampling rate that we have to sample, and what is the resolution. So we have to work whether it is 16-bit or 14-bit, what is the number of resolution we have to work, and what is the incoming signal frequency also, that matters. So like nowadays ADCs are available up to they are sampling up to 3 giga samples per second easily, or 36 GSPS they are sampling, giga samples per second nowadays are available. Intel FPGAs, they are releasing up to 36 GSPS. And incoming signal frequency also, whether it can be like X band, K band, Ka band. So up to that, the signal will come depending on the bandwidth requirements. We have to choose the sampling rate. And once the sampling is done, the signal is given to the digital part. So this is the intelligence intelligence that whatever the processing, whether it is for radar, we have to do signal detection, communication also we have to do signal detection, and for any image processing application, so the different algorithms will be implemented in the digital part. So basically, this is the typical system will look like this. So depending on our requirements, we have to customize the individual sub-blocks, and we have to realize those blocks as earlier we discussed, depending on the flow. If you take a typical VLSI based avionics system, so there will be like there will be front end radar will be there. So this will radar will be having different modes of operation. So air to air mode operation. So whether any enemy target is coming, or air to ground operation, like first in order to recognize the ships that are there, or any troops are there, and it should have electronic supporting measures, whether enemy is radiating any threats. So those things to be recognized by the EW suit, and so it should have flight control system. So it has to control all the air control the actuators, and navigation system. This navigation system will tell the system where the aircraft is. So it has to know where the aircraft is. So for that we need navigation systems, and if in the space, when you're in the air, so you don't know anything without this navigation system. It is difficult to locate yourself. So in order to go ahead, so we need to know where we are. For that we need INS GPS and some terrain avoidance systems we need, and we need to have some communication systems. So all these systems, as we are discussing here, so these will be realized by using the VLSI. So the dominance in the battlefield so will be decided by the effectiveness of these systems only. So in a fighter jet, so if you see a fighter jet, so the advancement in the technology depends on the individual subsystem advancement, how the system is effective, how the specifications are designed. So depending on that only, whether it is a fourth generation, fifth generation aircraft, or sixth generation aircraft is decided. So subsystems come to the design of those ICs that are realized. That one decides the capability of the weapon or aircraft, whatever it may be. So targeting and imaging systems we need, and head-up displays we need, and some cockpit displays. So nowadays advanced cockpit displays will be coming, so that pilot will be knowing everything in front of on his fingertips, and he can operate, he can complete the mission very successfully. And missile warning systems, if any missiles are launched against this aircraft, it has to warn the pilot, and pilot will start a countermeasures for that. And weapon control systems to fire a missile from the aircraft. He should have some weapon control systems, and he should have environmental awareness. So at what altitude he is, and at what ground he is flying. The synthetic aperture radar will be there into the aircraft, and this is if you take a radar system, like it will be having a many number of ICs, like phase shift attenuators, and some signal passing ICs. So all these things are realized by using our today's VLSI processing technology and flight data recorders. So we need to have a higher time to record the data. So we need to, as the flight time is higher, the capability of the system is more. So for that, like we need to have higher memory requirements. So all these things are possible by using the today's VLSI technology. And as we discussed just now, so we have like if you take any missile systems, these are essential for the country's defense or country's power. So various missiles are there. So as all of you know, there are like our IMD Integrated Guided Missile Development Program, IGMDP. So in that, so basically like they developed Akash, Agni, Prithvi, so Trishul. So these are the missiles. Now these are the 5 missiles they developed. So these are like, if you take a Agni missile, it's a surface to surface missile having the different capabilities, and these are like comes under strategic missiles. And Akash, if you take, that is for the defense of incoming aircrafts, to neutralize incoming aircrafts. Like they may be carrying any weapons and all. So to neutralize that, Akash weapons will be launched. And could be for, these are also surface missiles. So like this different class of missiles are developed, and now there are so many missile programs are going on in our country. So all these missiles will be needed different types of ICs for realization of their functions. Like if you like, we'll discuss those functions. And like if any threat is coming from outside the country, like ballistic missile, so we'll launch another missile against that missile, and this will go and it neutralize the incoming missile. So this the enemy missile may be carrying some nuclear threat or any other bombs. So this our missile will go and intercept. We have our air defense program is there. So air defense program will develop these missiles, and they will intercept that incoming threats. So this can be like endo atmosphere or exo atmosphere. So depending on the different class of targets that are coming, we will launch the particular interceptor, and this interceptor will go and it will neutralize the incoming threat. So based on the, so there will be ground search radars and tracking radars. So those radars will get the incoming threats at 500 kilometers onwards, and it will alert our command and control systems. So this control system will take a decision from which launcher the missile to be launched. So the particular launcher is activated, then the missile will go and neutralize the incoming threat. All these decisions, so which launcher to be selected and which missile to be fired. So optimum algorithms will be ran into the system, and the decisions will be taken. And that particular missile will go. For that missile also, it need to be continuously guided towards the target. So from its launching boost phase to terminal phase. So it has to be properly launched. Then only the missile will go and intercept. For that, it needs a lot of electronics, a lot of algorithms, a lot of processing capability. So all these things are made possible by using our VLSI technology only. So like there will be some IR seekers, not only processing sensors we need. So these will sensors will transmit and will receive. Whenever the target is near the interceptor, there will be proximity sensors. It will identify the proximity of the target, when to give the firing post warhead at an optimum time, so that the incoming threat is neutralized. So that for computation of those times, we need the proper sensors. So all these things, if all these computations, all these sensing functions are performed by our VLSI technology. And if you take any typical like air defense system, like Akash air defense system, so this Akash is meant for incoming aircrafts as well as helicopters. So there will be like a different troops will be there. So battlefield surveillance radar will be there. So different battlefield surveillance radar, it will surveillance for the targets, and it will give to the corresponding launcher. So the launcher will be fired against that particular target, and that particular target is neutralized. And so we are producing number of missiles, and these missiles are nowadays we are exporting also to foreign countries. And these missiles are used in for point defense application also. So like there are nowadays these warships are so more prone for the incoming anti-ship missiles. So these anti-ship missiles or anti-ship aircrafts will come and will destroy the ship. So in order to protect these ships, so another missile will be launched. It will cruise over the surface of the sea. So and it will go whenever near the proximity of the target, it will blast target will be blasted, so that the incoming threat will be neutralized. So for this, we need a lot of sensing and electronics. So all those things are realized in the country itself. Nowadays, we are realizing everything in the country. And so if you take a typical missile system, so there will be like inertial navigation system. So now this advantage of this is navigation system. So it will tell where the missile is. So then only we can decide where to go. So for that, we must know where we are. For that, we use inertial navigation systems. And there are GPS global positioning systems are there, but in a war scenario, it is there may be possibility that we may not get the access for the global positioning system, or it may be jammed. So for that, we will use inertial sensors. From that, we will sense our location, and we will determine our own position. So for that, we will use inertial navigation systems. And the guidance system will tell, after knowing my position, we can decide. Guidance system will tell where to go. So that is done by the guidance system. System will guide us where to go. And control system will give the control commands or actuators based on the guidance system, how where to go. So the control system will give the commands to our control panels, control surfaces, so that the control surface will be deflected in the required direction, so that the missile will be traveling in the required direction. And to perform all these things, we need some communication systems. So we need to send the data, telemetry data to the ground. So we have to send complete missile position, like complete missile health status, to the ground. what is the temperature, what are the vibration levels. Okay, all those things we need to transmit to the ground. So that is made possible by the telemetry data links. And this data link will tell, it's a communication between the ground as well as the missile, and it will tell the guide the missile from the ground radar data. So any commands to be given to the missile, so that will be done by using the data link. So data link for guiding, or if any onboard video is there, that we can transmit to the ground by using the data link. And this telecommand systems for giving any commands, any specific small commands to the missile. So telecommand system is used, like from if something happened, we have to give some self-destruction command to the missile. So such commands will be given by using a telecommand system. And command guidance system will guide the missile towards the target by using command guidance system. And if you come to, there are like various types of seekers will be there. There can be like active seekers, passive seekers, IAR seekers. So depending on the target requirements, the specific seeker is chosen, and the specific seeker is developed, and that is integrated to the missile. So all these things need a lot of effort. Integrating a subsystem into a missile is not a simple task. It needs you to take so many things into consideration, and you have to integrate, and it has to communicate with onboard computers. So all these things will come into picture. And if the missile need to travel at the lower altitude, so that the enemy can't see the missile. So if the missile altitude low, so it will be obscured in the clutter, ground clutter. So the enemy targets cannot see the incoming missile. For that, in order to travel at lower altitude, we use altimeters. Generally, cruise missile, they need these altimeters. These altimeters will be giving at what altitude the missile is going. Inside control system will adjust it control surfaces so that it will maintain that lower altitude. And these telecom systems, so these are used for terrain matching purposes. So with the terrain matching also, we can identify. So with the INS system, what happens is as the time increases, this errors will keep on increase. So this increase in errors will cause the error in the location locating the missile. So this can be nullified by using a telecom system. So what we'll do is we'll use this altimeter by terrain matching. If some hills are there, so we'll use by terrain matching algorithms, we can identify where exactly it is. So for that purpose, we use telecom kind of algorithms we'll use. And many sensors will be there on board. It can be like vibration sensor, temperature sensor, so pneumatic sensor, different sensors will be there. So they will sense the position of each of the subsystems. And we'll be using some electronic warfare systems also. So like we want to neutralize a incoming, like any radar system. So for that we need electronic warfare system. So the radar will be emitting some radiations. So this electronic warfare system, it will identify at what direction that the radar is, in the direction this missile will go, and it will neutralize the enemy radar. So for that we need electronic warfare systems. And this onboard computers is very important. It will control it's like controlling all the functionality of the missile is done by this onboard computer. It's like brain of the missile. So it will, for that there is a lot of software will goes into it. So for that dedicated teams, they will work day and night for realizing those softwares. And finally, the purpose of the missile is to take a payload, like a warhead, to the specified location. So that warhead neutralization, warhead detonation will be done by safety activation mechanism. This will give the pulse to the warhead so that the warhead will be blasted at the required locations. So this is the major subsystems. So for designing all these subsystems, we need electronics, all of you know. So realize design, development, testing. So we have to follow strict quality rules so that the successful realization of the successful deployment of the system. So we'll conduct a lot of qualification tests, then are followed by acceptance tests. So this will be having some environmental test as well as EMAMC test. So many tests for each of the subsystem will conduct thoroughly. So then only we'll qualify the system for the integration into the missile system. Then after that, that missile system will undergo a lot of phase checks. So after passing all those phases, the missile will be launched. So this is the the system that are used in the missiles. So now if you come to a communication system, so in military communication, VLSI plays a crucial role in enhancing security, speed, and efficiency. We have to take in battlefield quick decisions. So for that, we need communication is essential, and that communication must be secured communication. So for that, we need these ICs, and these communication systems are used for soldier to soldier, and so from soldier to military base, and network communication between drones, warships, and military base satellites. So this communication will happen between all these things, and the custom ASICs, SOCs, and FPGAs form the core of this modern military communication systems. So this VLS enables miniaturization of devices for lightweight and portable equipment. A soldier cannot carry a big equipment on his shoulders. So it should be very lightweight and it should be portable, and it has to work for longer times. And the real-time signal passing and faster decision making is essential for these systems. And these are enabled by using only VLSI technology. So as we know, go for lower nodes, we can miniaturize the system and we can have lower weight so that the troops can travel for longer distances. And it should be capable of sending like video, voice, and high-speed radar data over longer distances. So in order to send data for longer distance, we need to transmit higher power. So that higher power we have to transmit in efficient manner. So that will be done by using higher capabilities only, higher processing capabilities, or higher directional antennas only can be done. So that is possible by using the VLSI technology only. So antennas also can be integrated onto the ICs. So now ICs are coming with integrated antenna systems also. And hardware-based encryption for secure communication links. The enemy should not intercept our communication. So for that, we need hardware encryption is essential. That is very much important. And reduce power consumption for battery operated military devices. That is essential. So this communication can from ground to satellite or drone to satellite or any like armored fighting vehicles to satellite. All these things will be performed by using these communication systems. And for defense, radars is a very important part of the defense system. So for fighter jet, like radar, it works as an eye for the fighter jet. So you can see like incoming any other aeroplanes are there. So enemy aeroplanes you can detect and you can track, and if any incoming missiles are coming towards him, you can sense those incoming missiles. Or if any like warships are present on the ground, by using the SAR technology, you can identify the on the ground what ships are there, enemy ships are there. All those things will be done by these radars. So for the country of the safety, so we need such radars. So this will be keep on for every 24 hours daily. They will be searching for any incoming targets are coming, and it will alert and it will give our forces the information about the incoming threats. So these are like watchman kind of thing. Every 24 hours they will be monitoring the our boundaries. Our borders will be monitored. There should not be like no enemy should enter into our territory. So that is taken care by these search radars. After search radar, if it finds any target, so that cube going to for tracking radars. So these tracking radars will track the incoming threats. So there can be like multifunction radars. Some radars will work as a search radars and tracking radars, and they will track multiple threats. So all those things. Nowadays there are like boom in the phased radar technology. With the phased radar technology, you can active electronic scanning arrays. You can keep the electronic beam at any place, and you can track any incoming threat. So earlier we were using mechanical scanned arrays. Nowadays we are using the electronic scanning arrays. With electronic scanning arrays, we can position the beam at any location, and we can get the target data. So for this, we have to simultaneously we have to search for targets, and we have to track if any uh, the target is detected, we have to track the particular targets. So for this, we need a lot of computational capability. So all these computations algorithms are developed by using the modern VLSI technology only. So there will be like a beam controller will be there. There will be signal processor. So and displays for displaying about the target information. All this functionality will be performed by these ICs only. If you take a typical radar system, so there will be like front end, there will be like some RF front end will be there. So that will be having so phase shifters and detonators to active electronic scanning for doing that. So we need phase shifters. So with the phase shifter, we can position the beam in the space at any location, and we can instantly we can move the beam to any other location. Earlier, we used to use mechanically scanned arrays that are slow in operation and unreliable operation. So these will be reliable. Even a single element goes bad, so other elements will be working. So the operation will be reliable. Reliability of these systems are improved. So we can position the beam instantly at any place. So after this, we'll be taking the signal into, like, the signal will be transmitted, and whenever it hits a target, we will get the echo back. And depending on the echo characteristics, we'll identify the what type of target it is and at what distance it is and at what angle it is. So all that information will be gathered by these systems by having the processing capabilities, better processing capabilities. That information will be communicated to the some computers. So by using the Ethernet or whatever communication it is, where it can be RS422, all those things will be performed, or 1553 communication. So all that communication or transmission, sensing, control, all this will be done by these chips only. So radars need to transmit higher power to detect long range and small targets. So we have to transmit higher powers in order to long range targets, which are very small, smaller than a bird. So like nowadays, the technology is like stealth technology that will be having lower RCS. Even the big aircraft will appear as a small bird. So there is a technology improvements. For that, we need to have higher power transmission capabilities. That is possible by using developing the latest RFICs, which are having better efficiency, like gallium nitride. High power transmission possible by gallium nitride technology. So these technology will be having capability for withstanding of higher powers, as well as they are having higher efficiency. So they should not generate more heat. So it has to, whatever power given to it, it has to radiate only. So that is used, that should be useful for directing the incoming target only. So for that, we need gallium nitride technology. So this technology is where to like fine tune this technology so that the technology is developed. And need to have high bandwidth waveforms to resolve closely spaced targets. So if two targets are coming, we should not think that is a single target. So when they are very closely spaced, we should have high bandwidth waveforms. We have to resolve those targets even though they are very closely spaced, and we have to take appropriate decisions. Hence, high-speed analog to digital conversion technology is made possible by VLS technology. All these things are possible by VLS technology only. To process echo from above waveform, we need high-speed real-time signal processing algorithms as well as digital hardware is essential. So this is realized by using all of by VLSI technology only. Like it can be like ASICs or it can be like FPGAs. So all these things nowadays, FPGAs are coming system on chips. Like they're having analog to digital converters, also high-speed ADCs also on the chip itself, so that we can sample at higher sampling rate. It can be like Ku band, up to Ka band. These ADCs are available. So directly, so now the trend is less RF part and more it is going to the digital part. Most of the systems are miniaturization is done by integrating most of the RF functionalities into the digital block only. So that is made possible by using advancements in the VLSI technology. So we need beam controller communication is performed optically. So from here to here, so we'll do optical communication. For that, photonic ICs are developed. So it's a multidisciplinary area. So here there are RF design is there, digital IC design is there, analog IC design is there, photonics are there. So all these things are developed, required things are developed. So with the above technologies, target tracking and identification capabilities are improved. So with these technologies only, we can identify the target, whether it is single target or multiple target, or it is a small target or big target, and what is the type of target, whether it is a helicopter or aircraft or missile, so or drone. So all these decisions can be, we can take by having these processing capabilities. And low power radars are airborne applications become possible. So these radars, if you are using for airborne application, it has to consume very low power so that the vehicle will work for longer time. It can go for higher ranges. So if you take any fighter jet, it has to work for more time, and it has to go for endurance is very much important. It has to go for longer range and higher time it has to work. So for that, we need to consume very low power. So that is made possible by using the VLSI technology. And integration of AI for predictive analysis in radar became a reality with VLSI technology. So we have to integrate AI also. Now, in radar. So we have to, there is a lot of data processing is involved. We have to, it is a single target tracking or multiple target tracking. So we have to have different algorithms to be running for target tracking. So we have to do assignment of the particular target to a particular track. So we have to take so many decisions inside the system. So for that we need AI technology. So that AI technology integration into this radars is made possible by using the VLSI technology. And nowadays, the biggest threat or biggest advantage are the drones. Everybody, as we all know, so in defense, it plays a very, very significant, important role. So a spam of drones, so they can do anything. Like UAVs rely on VLSI technology for advanced functionalities. So these drones are used as a weapon. This can be used for surveillance. Okay, so for many applications are there for the drones. VLS enables miniaturization, low power consumption, and enhanced performance. So applications include for flight control, we need to have some IC, some system flight control systems. We need navigation system. We need surveillance systems. We need and secure communication systems. We need uh, hyperspectral imaging systems or synthetic aperture radars. So many things are data links. So these surveillance systems will be having so many payloads. Okay, so for all these things, we need high-speed ICs and better advanced ICs we need. So this VLS enables. So SOCs handle image and video processing for real-time target recognition. So we have to recognize the in real time whether whether ship is there or whether it is a aircraft. So all these things are possible by using the image processing and video processing technology. There will be like optical cameras will be there and IR cameras and hyperspectral imaging sensors. So all these sensors, we need to have a better processing capabilities. And AI accelerates for object detection, pattern recognition, and AI-driven decision making. So we have to take so many decisions, whether for autopilot design or for fire control system. So many decisions need to be taken. So for the all that will be done by AI-driven systems. And the real-time analysis of sensory data from radar, infrared, and optical sensors. So we analyze the data from the sensors. So that is made possible by using this technology. And transceivers support wireless communication protocols like 5G or whatever it may be. So advanced communication protocols, all these are supported by using the transceivers. So if you take 5G, so there will be like a digital beamforming technology is used. So for that, we need to have so many transceivers to be integrated in the lower space. So all these things are made possible by using the advancements in the VSI technology. And these drones will be communicating to the satellites, and we should have ensure we should have secure communication links, and those links should be like tamper proof or they should not be intercepted by the enemies. So all these things are possible by using this technology, and they should be having low power VLSI based RF transceivers for longer communication. So we need all this. And for armored fighting vehicles. So this is essential technology. So for this technology plays modern armored fighting vehicles. So it enables miniaturization, power efficiency, and for wheelers enables it. And high-speed processing systems like fire control things and communication things, navigating and active protection systems. So in active protection system is a system. What it will do is if any enemy fires any anti-tank guided missile or any like kinetic energy weapon or any high energy weapon. So this active protection system will detect the incoming threat, and it will fire a warhead, blast warhead kind of thing, and it will neutralize the incoming threat at like 10 or 15 meters, so that the incoming threat won't neutralize this tank. So there is application of active protection system. So for that we are for that it needs some radars and so all these capabilities are like for in order to survive in the battlefield, we need to have all these technologies. So if you have these technologies, you will be having the speed in the battlefield. For that, we have to develop all these systems. So it will enhance precision of weapons using the sensors, rangefinders, and ballistic computers. So they'll be having some rangefinders. So at what range the enemy is there, so we'll identify the range. So there will be like laser rangefinders, and there will be some IR sensors will be there, and some computers they'll compute at what angle this gun angle should be there, so that it will the bullet will be neutralizing the enemy bunkers. So ballistic computers. So all these computations will be done by the our process. High-speed signal processing, sensor data with data. So custom ASICs. So we use like custom ASICs, we develop custom ASICs and FPGA algorithms, and that will be put onto FPGA for image recognition and targeting the enemy, and real-time data handling for rapid decision making. So we have to process the data in real time. So we cannot acquire the data and process offline. That is not possible. That we cannot offer in the battlefield scenario. So the data need to be real time processed. For that, we need to have so high processing capability, and we should have 360-degree battlefield awareness. It's not possible like only I look at the front. It's not like that. We have to see all the 360 degrees, and we should have awareness what are the threats that are there on 360 degrees. And so AI-powered data fusion algorithms we have to implement, and we have to recognize the threats and we have to neutralize the threats. All those things are possible by using this IC technology only. And this armored fighting vehicles with adaptive algorithms for jamming, detection of electron countermeasures. In the battlefield, it may possible like somebody may be jamming our systems. We should have capability to countermeasure those things, and we should effectively use our electromagnetic spectrum. So for that, we need better processing capabilities or high power and low bandwidth or high bandwidth waveforms. We should adapt to the scenario. So we have to sense the environment, we have to adapt to a scenario, all those capabilities should be present. And that crew should having the proper displays and all. And it should have active electronic system, so it has to protect the tank from the threats. And we need this defense satellites will play a very important role for safeguarding our countries. So defense satellites play a major crucial role in modern military and strategic operations. So these satellites support functions like surveillance, navigation, communication, and early warning. So all these functions will be done by these satellites. There are multiple satellites. Each satellite will be performing multiple functions for in a given mission scenario. So the purpose is monitor enemy activities, any troop movement or infrastructure movement. So all these things will be monitored by these satellites. So if any enemy troops movement is there, then we have to take the counter things like moving our troops in ahead or deploying our weaponry. So all those decisions we can take by monitoring the enemy activities. And uses high resolution cameras, hyperspectral cameras, and radar imaging for real-time tracking of those enemy movements. So alien systems, payloads for intercepting enemy radar and communication activities. So enemy will be communicating, so for intercepting his communication links, or what are the enemy radars are there. So in order to understand enemy radars, we need alien systems that are onto the satellite that are integrated. So there is a concept called SEED, suppression of enemy defenses. So we have to suppress the enemy defense so that our activity. So for that need so these supportive systems we need. So secure communication for armed forces relays voice and video data and provides accurate location and navigation and timing for military missions. So accurate location finding for it can be like for UAV, it's very accurate location information. For that we need these multiple satellites. These satellites will send the give the information about their own location so that they can take the guidance commands and supported guided missiles movement and detects incoming ballistic missiles and nuclear threats. If enemy fires a ballistic missile, so if a satellite is there, it will detect very the boost phase itself. It will detect and it can alert our interceptor missile so that we can take corrective action early. So as much early if we are taking, we can neutralize that much effectively. For that, these satellites are very much essential. And uses infrared sensors to track missiles launches and alert defense systems and improve the accuracy of missiles and guided ammunition, as we saw. So for a surface-to-surface missile, that missile has to go and it has to hit the target very much accurately, less than 1 meter accuracy we need. So if the accuracy is poor, if we are hitting the target 10 meters away, so there is no use. We should have a better precision of accuracy, better precision and as well as accuracy. That is made possible by using these satellites only. They will give the exact location of that missile, so that they can precisely neutralize the bunkers, or it can be enemy installations. Use real-time navigation data to guide us to target with precision. So they will use real-time data. So whatever data that is coming into the thing is possible by using these IC technologies. So IC technology plays a major role also. So these ICs need to work in harsh environments like radiation radiation will be there. So radiation hardened ICs will be there that work at very high temperatures or very low temperatures. So all these things are possible by using this technology, ICT. And so for naval systems, so there will be like so in ours there the today's weapons are and ways to improve control and detection systems. And we need passing advanced DSPs are used for sonar detection and guiding the torpedoes. We need so much for real-time trajectory prediction, trajectory implementation. We need these chips and miniaturization. So size, weight, we have to compact designs like underwater they cannot travel at higher speed. They will go to very lower speed. It will take higher time. So these ICs should be working very efficiently for those missions. And power efficiency, we should have low power efficient designs. So low power will say design extends battery life so that the targets will work. So like we are having different weapons. Underwater systems are like torpedoes for against ships. So against warships, so they can be launched from the submarines. And underwater drones. So uh, underwater anti-submarine rockets and depth charges. So this will be depth charges are released from a helicopter. So this will go onto the ground, like underwater, and it will go and it will neutralize a big warship. So these are depth charges are required. So they will be having each of these systems will be having its own electronics, and the design of these electronic systems are specific to that application only. And underwater projectiles. So so these projectiles will go and neutralize any submarine or any warship. So these are the different technologies that are defense technologies that are needed. So in conclusion, so the VLSI plays a very much big significant role in realization of these defense systems and complements in completion of our armed forces missions with high precision. So this is the main objective of the VLSI technology. So these are the things. Like if you have any queries, you can ask any queries. Thank you. That's all from my side.
Thank you, sir.
Yeah, thank you, ma'am.
Sir, let me ask the participants if there are any queries. We'll go ahead, sir.
Yeah.
Participants can raise your hands if you have any queries so that we will be unmuting you.
Usha ma'am, you have raised your hand. You can ask question.
And one more is also there, sir. I think they are unable to unmute it. SK.
Hello. Hello. Can you hear me?
Yes, sir. Audible, sir.
Yes, sir. Yes, sir.
Yeah. Yeah.
So this is Dr. SK Kundu. This is the nice presentation by Dr. Sir, can you tell me what is your contribution as a DRDO scientist in Tejas and the advanced medium combat aircraft in terms of the VLSI design? Your contribution.
So actually, I work for missile applications, not for the aircraft applications. Actually, like each of the science teams will be working for different applications. So I am specific to missile applications. Tejas is done by Bangalore team. So they develop Tejas aircraft for that different subsystems they develop for whatever we discussed. It can be communication systems or electron warfare or radars. So all those systems will be developed by aerospace teams. Our contribution towards the missiles.
Only missiles, your contribution towards the missiles. So in missiles, what are the different components you are producing?
We are developing missile-borne radars, miniaturized radars. We are producing onboard computers. We are producing inertial navigation systems. We are producing telemetry systems. We are producing data links. We are designing and developing missile seekers. We are developing infrared image seekers. So all these subsystems, proximity fuses, so radomes, all these systems are developed by our teams.
So at a general question, sir, are you working in GAN device?
Yeah, our team is working on the GAN devices. There is a solid state physics laboratory, SSPL is this. So the laboratory is responsible for development of GAN devices.
One last question, sir. What are the different devices produced using GAN at your laboratory?
So GAN, so we develop power amplifiers. So the power amplifiers can be it can be 1 watt application or 10 watts, 100 watts. Like this, there are different classes are there. So depending on the application requirement, so different power amplifiers will be produced. So this power amplifier, after producing the power amplifier, we have to package it properly. So thermal design is very much important for these power amplifiers. So that complete module they will develop and they will give for that any requirements are there. For that requirements, they'll customize and they'll give it to you.
Sir, this silicon carbide material can be used as a high power reconfigurable antenna. Silicon carbide, SiC.
Yeah, silicon carbide we can use as a substrate, dielectric substrate, or we can use it as a radome. So we can use
So the power and high power can be used as a high power or high bandwidth, sir.
So we can use for low loss. There is one laboratory called Defense Metallurgical Research Laboratory. So they will develop this silicon carbide, silicon nitride, and ceramic technologies. And so those things will be developed by our laboratory. So that laboratory is responsible for this. And these technologies can be used as a radome or it can be used as a substrate. So we in one of our project we are using as a radome for ballistic protection. So it should protect bullets, incoming bullets, and it has to protect the internal electronics. So for that we are using this silicon carbide substrates. And it is having better thermal properties also. Yeah. Okay. Welcome.
Thank you very much, sir.
Yeah. Welcome.
Is there any participant, anybody is having any queries?
Participants can post the questions into chat box. Ma'am, I think no questions, ma'am.
Yes, sir. So, Rajendra Garu, thank you very much, sir, for your presentation and readily accepting our invitation. So, thank you so much, sir.
Yeah, thank you all for your
Yes, sir. Yes, sir. Now I request Dr. Vasudev Bevara, FDP co-coordinator, to give his concluding remarks.
Thank you so much, ma'am. And good evening, Dr. Rajendra sir, and good evening to our principal sir and our HOD Jagan Navin sir, and good evening to all of one and all. On behalf of the organizing team, I feel privileged to propose the vote of thanks for the first session of this 6 days ATAL Faculty Development Program on VLSI Design Innovation for Defense Application. First and foremost, I extend our heartfelt gratitude to Dr. Rajendra sir, our esteemed speaker, for his insightful and engaging session today. Sir, your experience and profound understanding of VLSI innovation and their critical role in defense application have enlightened us all. At the same time, in this first session, you are explaining a very excellent, and you are giving a wonderful knowledge about VLSI, how it will be useful in defense applications like armed fighting vehicles and missiles and battle ships and underwater torpedoes. Each and every session, really, to be frank, every slide is very useful to give you wonderful knowledge, and it will very useful to give you a good bridge between the academics and the defense systems. And in future also, maybe a lot of faculty members will be do a research on this VLSI design using in defense applications. We need your suggestions, and at the same time, 1 second. Your session has truly set the tone for the rest of the FDPs, and we are deeply appreciative of the time and effort you have dedicated to sharing your knowledge with us, sir. I would also like to express our sincere thanks to our principal for their constant support and guidelines in organizing this event. At the same time, I would like to express our sincere thanks to our HOD, Dr. Jagan Navin sir, for their constant support and guidelines to organize this event. And your encouraging has been instrumental is making this FDP a reality, and your vision continues to inspire us to academic and technical excellence, sir. Thank you very much for giving this, for accepting our uh, uh, very much. Thank you, sir. That's it, sir.
Welcome, Vasudev. Yeah.
Thank you, sir.
So I'm delighted to come in front of you all people and sharing whatever knowledge I have. So I always welcome if you have any queries or if you have any like association with me, always you are welcome. So I have my contact details are with Vasudev. You can contact Vasudev for my contact details. Thank you all for your participation in the program.
Thank you, sir. Thank you,
Thank
sir.
you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir. Thank you so much, sir.
Thank you.
Sudhendra Kumar, sir. Sir, good evening, sir. Sudhendra Kumar, sir, can you able to hear me, sir? Sir has joined but unable to speak out. Sudhendra Kumar, sir, shall we start the session,
Madam,
sir?
ID, please.
Yeah, SK Sudhendra Kumar.
Ma'am, is there in meeting only?
Yes, sir. Yes, sir. Sir has joined.
Make him as present, Ranil.
Sir, he is present only, sir. Sudhindra Kumar K.
Yes, sir. Yes, sir. Good evening, sir. Sudhindra Kumar, sir.
Okay, madam, fine. Thank
So next speaker has come. So we'll start the session 2. So good evening, sir. Sudhindra Kumar, sir. We welcome you for this 6-day online FDP on VLSI design innovations for defense applications. So now I request Dr. Geetama, Associate Professor of EC Department, to introduce our guest.
Yeah, thank you, ma'am. Good evening, sir, Dr. Sudhindra Kumar. Good evening to all participants.
Good evening to
It's my
everyone.
pleasure to introduce today's resource person, Dr. Sudhindra Kumar K. Dr. Sudhindra Kumar received BA degree in Electronics and Communication Engineering from VTU Belgium, MTech and PhDs from NIT Rourkela. Presently, he is working as Associate Professor and Domain Head VLSI and Embedded Systems in PES University, Bangalore. PES University, Bangalore. He worked in various industries like Wipro, Biom, GT Enterprises, Qualcomm from the year 2004 to 2012. In the field of research, Dr. Sudhindra Kumar has successfully executed over various sponsored projects, including the VTU Research Grant Funded Research Project and Department of Science and Technology, Government of India Funded Research Project, etc. He also handled 6 consultancy works with the government and other companies. Dr. Sudhindra Kumar has an impressive portfolio of academic contributions with 28 publications in various international journals and conferences. He also guided the 2 PhD scholars. His research areas include system on chip design, hardware security, and mitigating counterfeit ICs. He has Institute Industry Connect programs with various organizations like Qualcomm, Intel, Cadence, Intel FPGA, Telebrahma Technologies in Bangalore, and COE IoT Lab Software Technology Parks of India. Thank you, sir. Sir, Sudhindra Kumar, sir, now you continue, sir.
Madam, thank you very much for the generous introduction. Just a second, I will share my screen and I will start my presentation. I hope my screen is visible and I am audible, right?
Yes, sir, visible.
Yeah. And actually, the topic given to me is mapping algorithms to architectures. It's a very classical area of research from last, we can say, around 70 years in VLSI, or especially not in VLSI, basically in the electronics engineering. And basically I cover, I don't want to be, and I think most of the people here are faculty, it seems that the people attending the maximum are from faculty, and also there may be a research scholars in the audience. So my basic worry is that already most of us know the textbook called as VLSI signal processing from Keshav K. Padi. So that's what exactly the mapping algorithms to architectures or anything, something like that. The question is the general tendency, the very general tendency for any person who is working in VLSI. We teach digital VLSI from Neil Westre or Rabai or anybody, and we study analog VLSI from Razavi, etc. and all. The question is, if I want to do PhD or if I want to do research, what should I do? The fundamental thing is that, okay, implement FR filter on FPGA. It starts with that actually. So let's go deep into that so that we'll map the whatever the algorithms we study, image processing algorithms, video processing algorithms to FPGA architecture or VLSI architecture. This is a general tendency of any ECE background who have studied reasonably, who has got a very good reasonable basics in signal processing and communication engineering will have a tendency of implementing communication techniques or signal processing techniques on FPGAs or any other such kind of or on ASIC or Verilog simulation, Verilog implementation, etc. In the last 4 decades, starting from 1984, it's a very people are still continuing the mapping the algorithms to architectures, making the algorithms work on real hardware. Very recently, I gave one keynote in one of the industry forums. Is that why AI now? The topic was why AI now? Why artificial intelligence now? One of my professor at NIT Rourkela, who taught me during my master's and PhD, not my PhD, during my master's 20 years back or 18 years back, he passed away 8 years back or 10 years back. He passed away at the age of 75 or something like that. But he got retired in 2010. He did his PhD in 1977. He did his PhD in 1977 from IIT Kharagpur. His PhD thesis was Odia character recognition using artificial intelligence. In 1977, he did a PhD on artificial intelligence. So artificial intelligence is not new, but why it is now? Why the AI becomes more important now? Even though the AI was there in 1950s, one of my teacher did a AI PhD in 1977. Why the AI boom now? Why the people talk about the AI now? The question is, hardware is available which can run the AI algorithms faster, and which can make the AI driven applications in real time. So we get the result. Earlier means 20 years back or 10 years back even, we didn't have a computers which can run the AI algorithms efficiently and give the results with a minimum latency or with minimum time. There were no computers at all. So gradually the world, the people designed the computers to run the AI and ML algorithms efficiently gradually. So it became not at 90 nanometer technology, not at 45 nanometer technology, not at 16 nanometer technology. We gradually, in the submicron technologies, it is getting possible. That is basically the submicron means below 45 nanometers. We are able to get some AI working in the hardware, AI working on the silicon. So because why AI boom now? Because there are processors and there are chips which can run the AI algorithms in real time and give the results in real time. Otherwise, if AI takes 3 days to produce the result, nobody will rely on AI. Nobody will run the AI algorithms or AI products won't be existing in the market. So already in last 10 years, there is a good amount of research already done on AI. The AI ML is something more or less like I think the most of you people know maybe knowing about it. It is a systolic array architecture, and again configuring the systolic array architecture in different ways and different dimensions and in different directions, so we can make the AI algorithms work. The bread and butter of running AI is a matrix multiplication. The AI matrix multiplication works on systolic architectures that we all of us know. Most of the GPUs, most of the Google TPUs work on systolic arrays today. So the question is, already the people have saturated. If somebody want to do research to now. Somebody says that FPGA implementation of some ML algorithm, then I strongly discourage this because it's already saturated and there is no low-hanging fruits there, no easy problems to solve. Innovation is already done, the gap is already filled. If you want to do PhD in FPGA architecture for AI algorithm or ASIC architecture for AI algorithm or some VLSI implementation of AI algorithm, I strongly discourage because already a good amount of work and good work is done already. So then what next after AI architectures? Where exactly the mapping algorithms to architecture is can be applied, in which areas, where exactly, what exactly is the conclusion topic of this lecture, this lecture or this session, something like that. So generally I have this few things to go with. This is the briefly a content. At last I added, yesterday night I added about defense requirements because I found it something, this FDP is connected with something defense also. So that's the reason why I made this last addition as a defense requirements, etc. So before getting into this one, the world has become heterogeneous. The world has become heterogeneous. What do you mean by heterogeneous, homogeneous, and all? But basically, we all know the history of a computer architecture. In 1986, the first RISC machine came. Before 1986, it was all CISC machines. That is complex instruction set. Just a second. One second, I will be back. Okay, sorry. So why this heterogeneous architectures become very, very evident after 2014? The answers are like this. If you look back into the history a little bit, the first RISC came into the existence in 1986, somewhere in 1987, when the ARM started to design the RISC process or ARC process. The question is, after, okay, innovation was designing a computer or processor, that is done. Now we did a RISC, that is also done. Then what next? Do the pipelining. Then we did the pipelining for 10 years from 1990 to 2000. 3 stage, 5 stage, 6 stage, whatever the stages, 17 stage, all stages done. Then what is the next computer architecture? CISC came, RISC came, pipelining came, then what next? Make dual core. By 2002, 2003, we started getting dual cores getting designed. Then again quad core, then again octa core, then 64 core, then 128 core. Now the Xenon D, Intel Xenon D is a processor with 128 cores generally used in cloud centers, data applications, data centers, Facebook, Amazon, Microsoft, etc. The question is, yes, 128 cores we have done. Then what next? Then what is the next incremental thing what we can do improve the computer architecture? Okay, first CISC, then RISC, then pipelining, then multi-cores, homogeneous multi-core, same copy, core 1, core 2, core 3, core 4, till core 2, 127. Fine. Then the next what? Next is heterogeneous. Heterogeneous means I don't want the same core to be there. I want an hardware accelerators to be there. Hardware accelerators means I need a one DSP processor, I need a one ML accelerator, I need a security processor. I need some 10 cores inside my computer, 10 processing cores. But just like a quad core, octa core, they should not be same. I want a different course, a different course need. I will need it. So why we arrived at this problem? What is the fundamentals why we arrived at this problem? Because the three laws driving the computer architecture failed. Three important laws which the failure of the three important laws in the recent in the last 10 years very precisely made us to innovate or get into the heterogeneous computer architectures. Otherwise, if these laws would have been hold true for in last 10 years, we would have not invented the new architectures in the heterogeneity. That is with GPUs. I have a CPU, I have a quad core CPU, I have a GPU, I have a hardware accelerator for signal processing, I have a security block, I have a image processing block separately inside my processor, etc. And all this we would have not done at all. If these three laws would have hold true. We would have done all these things in the software itself. Because of these three fundamental laws failed, there was no innovation possible in software, so we have to do it in hardware. We are forced to do the hardware changes and get the heterogeneous computing where exactly the mapping algorithms to architectures make a difference. So what are those three laws which failed? One is a Moore's law. We know this is the blue line shows the Moore's law prediction, and again this is the red line is actual. You can see the gap by 2015. The gap has increased significantly. So you cannot, there is no free lunch. The free lunch is over. Reduce the transistor size, reduce the channel length, have more transistors on the chip. You say that it is much faster, much functional, more functions at much faster, and sell it to the customer. That free lunch is over. So the Moore's law, there is a lot of gap between what it should be and what we can do. So by the 2014-15, so the Moore's law failed. Then again, there is something called as a Dennard's law, which is called as a power density law. You can see this graph. Here I have a nanometers in the y-axis, and then the x-axis is years, and the y-axis is relative power per mm square. Relative power per mm square. So this rises like this. This means you can see this at the year 2000 at whatever the nanometer technology we had on that day with 180 nanometer technology maybe C and all. So we had that time the power was somewhere around 0.5 nanometer square was the power density. Gradually you can see in 2002 it was still a stagnant. You can ask a question, what was it was up to 2000? 2000 it was straight line. From the 1980 to 2000 it was a very flat straight line. Basically it was a flat straight line. Even though you increase the number of transistors on the chip, the power density never increased. Power density was constant. That is called as a Dennard scaling. Dennard scaling says that the power density stays constant so that the power use stays in the proportion with the area, both current and voltage and current scale downward length. So this is the Dennard law. But after 2000, even though we scaled down the voltages and currents, the power density slightly started increasing linearly. And after 2006, with 65 nanometer and below technologies, it increased exponentially. Basically it started exponentially increasing at somewhere around 45 nanometer technologies, or even 65 nanometers technologies had its impact. Some impact was there, like NBTI effect and all, but at 45 nanometer technologies it was a solid increase in the power density. We can say this power density never been a constant. It's kept increasing exponentially with the technology scaled down, and when the technology keeps scaling down with the years, the power density kept on increasing. So the transistors getting heated, thermal breakdowns, yield reduction. We had a hell lot of engineering problems there. The problem is thermal runaway, energy cost, yield, this one, etc. So basically, why this happened, why the Dennard law failed, why it is not constant, why it is exponentially increased. It came to the basics again because of the dynamic power consumption increased significantly, the leakages increased significantly, and then ideally the static consumption of CMOS is zero, but the leakage increased significantly. Dynamic power increased significantly due to the higher parasitics capacitances, higher parasitics and all. So that's the reason why the Dennard's law failed. Then the third more important, what are the effects of Dennard's law failure? Dennard's law failure created hotspots inside the chip. It leads to the thermal breakdowns. It went to a lot of other reliability issues with respect to the operation of a processors and voltage regulators. And finally, there was a yield loss during the production, which is a significant. It was eating into the significant profit margins of the semiconductor companies. So then finally, the last law which really made the failure and which made the world to move towards heterogeneity from the homogeneous process is Amdahl's law. So it's a formula which gives a theoretical speed up in latency of the execution of tasks at fixed workload that can be expected of a system whose resources are improved. Let's leave the English jargon here, then look at the graph. Look at this graph or the analytical picture to understand what exactly the Amdahl's law and how it has got failed. Let's assume that I have a processor, I have a CPU with 65 cores, or 64 cores or 65 cores. 64 core CPUs I have, and I have kept them 99%, or I have kept them working all the time. I have kept them working all the time. I have given work to the all the process for 99% of the time. So only 1% I am not utilized. 99% I have utilized. I have 99% I have utilized all the process, which is ideal case, which is almost impossible. And again, the multi-core processors are nightmares for the multi-core processors are nightmares for the multi-core processors are nightmares for the software designers, because if you ask the software designer to write a code, he can write a code, he can write a piece of code, but if you ask him to make it as a multi-thread, yes, his problem starts. He has to break the problem into several pieces, then again he has to write a multi-threading, then he has to connect it them properly, then again you have to run it on the multi-core processor. So it's not easy job, it's a nightmare for any basic software engineer who is working in device drivers, kernels, etc., and all, operating systems and all. It's a nightmare for a fundamental software engineer to write a software for multi-core processors. So it's a tough job, but even I achieved something ideal thing, which fetches Nobel Prize for me. That is 99%. I kept all the cores busy, 1% is unutilized. Even in that case, I get 35% to 36% speed up. That's all. To get the 30% speed up or 35% speed up, I have to keep the 99% of all my cores, 99% of the time, all my 64 cores working. It is almost impossible. Most of the times, we keep 90% working is the ideal case. Means with all the difficulties in software engineering, I can make my course, all the cores working 90% of the time. If I 10%, I am unutilized. So 90%, if I keep all the cores, all the 65 cores working, the speed up is 5%. To get the 5% speed up, you have designed a processor with 64 cores, how much complexity it is, how much time it will go, how much verification it will go, how much cache management you will do, how much memory management you will do, how much low power you will do, hell lot of engineering you will do to get the 64 cores processor working. And again, you are able to make them best of the best case, you will make the 90% of the time utilized, only 10% unutilized. Even if you are 10% unutilized, 90% you are using all the processors, you will get at the overall, at the macro level, at the system level, you will get 5% increment in the speed. For the 5% increment in the speed, you are spending too much of engineering, too much of production cost, too much of testing cost, too much of software engineering cost. Not worth. So Amdahl's law failed. Amdahl's law is that it says that even if you do 54 cores or 128 cores, and if you run the 90% of them working very well all the time, you won't get much speed up or much performance improvement. So this is all the Amdahl's law. Amdahl's law, the Dennard's law, and Moore's law. These are the three laws which made us. Then the question comes: if the Amdahl's law is failing, the power is a problem, Dennard's law, Moore's law is no more working, then how to improve the computer architecture? How to improve the performance of a computer? Then what are the innovations we have to do in the computer architecture? Because Moore's law free lunch is over, power density problems are there, Dennard's law failed. Adding another core, I had a 8 cores, now I will go with a 16 cores. Next time I will go with a 32 cores. No, now I have a 128 cores, then I will go for a 256 cores. Then after that I will go for a 512 cores. Then after that I will go for a 1024 cores. Don't work, because Amdahl's law clearly says that even if you increase the number of cores, if you are running them with 90% capacity, you will only get 5% performance improvement, which is negligible for the end user. So now all these flaws came. You cannot add a core. Moore's law. Moore's law is failed. You cannot add a core. And adding a new thing, any new changes in the frequency, I will play with frequencies and all. Then your Dennard's law is a bottleneck. Thermal breakdowns will be there after a point. Then how do you improve the computer architecture? How do you improve the computer architecture? The only answer is the only answer is going for a heterogeneous computing. I hope I made a point. Any questions you can ask. I don't know how many are listening. Only don't know. If you have any questions, you can interrupt me in between, and also you can ask me now. Take a minute and ask me the questions if you have any queries.
Participants, if you have any queries, you can post a question to sir.
Or else you can chat and put it in a chat box. In the last, we can take a pause. That is also fine. Yeah. Fine. Okay. I think I made a point that why heterogeneous computing required, why we need hardware accelerators. And again, if you, frankly speaking, in 2006, 2007, 2010, in 2012, if somebody doing PhD in mapping algorithms to architecture, if I say somebody, I'm working on a FR filter, I'm working on a FPGA implementation of a FR filter. If somebody says I'm working on a FPGA implementation of a image processing algorithm, I simply disencourage them. Now, my fundamental question is: you have a DSP processor. If you can run a FR filter efficiently on a DSP processor, more efficiently with a less amount of engineering, then why you are going and doing it on FPGA? And again, it does not give any great performance at all. FPGAs are costly. I'm talking about 2010, 2007, 2008 and all during my masters. I strongly discourage the people who do PhD in mapping algorithms to architecture, because you have a DSP processor available, you have a strong ARM processor available. Why don't you do the FR filter on ARM processor and get your job done? Then why there is a requirement to do the FPGA implementation of FR filter? There is no engineering necessity at all. Till 2013-14, it was the same argument. Why if you have an ARM processor, if you have an efficient, strong process, why you want to design a hardware for a complex algorithm? Do that complex algorithm in software, then get the job done. That is what the world way. That was the way of the world till 2013-14. And nobody bothered about FPGA implementation of a video processing algorithm and all, except some crazy academics in IITs and NITs and some crazy universities abroad. But now after 2015, the textbook VLSI signal processing by KK Padi has got a more importance because of the failure of these three laws. Now we have to learn the mapping algorithms to architecture more efficiently. So that was exactly the, now it is required. From 2016 onwards, it is required to build hardware accelerators and integrate them with my process in my laptop, in my mobile phone, etc., and all get the job done. So this is what are the future aspects of computer architecture. There are a lot of things are there. For example, very widely discussed, at least 10 papers to 30 papers, 50 papers get published every month in different journals and magazines. That is a VLSI architecture for some particular AI algorithm, VLSI architecture for some particular ML algorithm. Yes, the job is done. Already we have a very powerful NVIDIA GPU, a very powerful AMD processors which run AI algorithm efficiently already there. Then what next? Before we get into the what next here, there are few areas where we can still do the improvement with respect to AI. Look at this graph. Look at this graph. The graph is something like this. See, this is the Python. If you run on my laptop or any other workstation, if you run the Python, if you have your speed is 1. Your speed is 1. If you are using a Python code, for example, let's take a FR filter or else FFT algorithm or else some sorting algorithm also. Let's take a simple bubble sort. If you implement a bubble sort in Python, the speed is 1. That's a benchmark. If you implement the same bubble sort in C, you will get the 47 times faster running algorithm. Then if you use the parallel loops in the data using data structures and all, you will get a 366 times better speed. Then if you do the cache memory, L1, L2 cache memory optimization, reading into the memory, writing into the memory, if you optimize it, then you will get 6,700 times faster. Then if you use this historical array to run the sorting algorithm, or else if you make a dedicated hardware for sorting algorithm, you will get a 62,000 times faster than your normal Python code. So this made the people to, especially this is for matrix multiplication. Sorry, it's not for sorting, it's for matrix multiplication. This linear line applies to the sorting, even for FR filter, even for any image processing algorithm. So this, if you run the matrix multiplication in Python, the speed is 1. If you use the dedicated systolic array architecture to run the matrix multiplication, it is somewhere around 60,000 times faster than your Python. That's the reason why we need a custom architecture today. Earlier, the speed up was not there. The speed up was not there in the earlier cases. Now we got the speed up in these cases. That's the reason why we have a hardware accelerators is a necessity. Going back to the VLSI signal processing, KK-PADI is a mandatory thing for somebody working in a computer architecture. The guys who are my computer science friends are there, my even ECE friends who work in computer architecture, etc. and all, they never study VLSI PADI because they say that we are computer architectures, not signal processing designers. No, now they are studying signal processing architectures, VLSI signal processing by KK-PADI. The simple reason is the future computers cannot be designed without mapping algorithms to architectures, especially AI-enabled architectures. That's already done now. That is done and dusted. So now with this done and dusted case, with this domain-specific architectures, where I design a architecture for matrix multiplication, I design an architecture for FR filter, I design an architectures for image processing, I design an architectures for cryptography. This is a domain-specific architectures became reality, which was, if you say about any domain-specific architectures 20 years back, the industry would have seen the crazy academic people will do a lot of things. The crazy academicians will keep doing this mapping algorithm to architecture because they don't have any other job. They just need a papers, so they keep doing it. If you have algorithm, implement it in software, it is running at the same speed as your FPGA, then why I should worry about it? No, those days are gone. Even industry adopts the mapping algorithms to architectures. They design a lot of GPUs, a lot of software-defined networks, a lot of tailor-made specific class applications, architectures for tailor-made specific class of applications called as accelerators. The world is moving on in this direction. So if you look at this, a domain-specific architecture, it's basically a systolic array. It's a SMID architecture, means single instruction, multiple data. Some single instruction will work with multiple data. MIID means multiple instruction, multiple data. It works like this. Then, which we know already. Why I'm not getting into these details? Because we know all these things in our UG studies or PG studies. So apart from this domain-specific architectures, what are the problems with the domain-specific architectures? Basically, these domain-specific architectures will fail until unless you are not using the very recent NVIDIA GPU or AMD GPU. When AI fails, AI even running a large AI algorithm on these architectures fails, especially the Google TPU and all. Why? Because the data sets are very large and caches won't work very well. The caches won't work very well because compilers won't work very well. We don't have a compilers, just like a Borland C compiler for x86 in 1997 is more efficient than a compiler which is meant for GPUs today. Because handling a cache, handling a compile time is handling a caches at a compile time is not an easy task, even for a very expert compiler design. So the caches should work well. Locality is very high, meaning by definition, most of the cache is idle most of the time. But whenever really there is a traffic jam, there is a traffic jam in the cache. Most of the times the road is vacant, but when there is a rush, there is a mad rush. There is a mad rush. This also happens in this domain-specific architectures, especially in architectures based on systolic array, which meant for running AI and ML algorithms. That needs to be addressed. The people have addressed it in very recent GPUs and in both AMD and NVIDIA. So what else? What exactly we can do? The question is, does this domain-specific architectures were not there? Yes, domain-specific architectures were there as early as before 1996. If you look at the fuzzy logic accelerator and with 3 instructions in HCS12 or HCS12X and in HCS12 from Freescale semiconductors for the automotive application, yes. The fuzzy logic accelerators was there in the HCS12 as early as 1996. It's that. And again, discrete cosine transforms are already available in TI DSPs as early as 1999. So this heterogeneous computing was there very early, but not in a large scale as it is required today. So we don't want multi-cores today. We need a process with GPU integrated, with hardware accelerators integrated, with security accelerators integrated. I don't want a plain for quad core, octa core, 32-bit, 32-core processor. It's no more works for me. I need a heterogeneous computer which has got all these features. Does this features new? No, it was there already 30 years back. So this is the Google TPU example because just I want to talk about the AI a little bit. So this is the matrix multiply unit, systolic array control. This is where exactly the systolic arrays are implemented. And the rest is activation, the functional organization of Google TPU. The details can be seen in the Google TPU version 1 data sheet and all. So I'm not getting into the FIFOs are there, DDR interfaces, caches, systolic array control, and matrix multiply unit. Yes, as a classical architecture to run the AI algorithms. This is done and dusted now. Then what next? Then what next? So before getting into the what next, we have considered 2 different approaches to improve the program performance by improving efficiency in the use of hardware technology. One, using an high-level languages, just like Python, etc., and all our transformers or LLMs, large language models, etc. The second, by building the domain-specific architectures that greatly improve the performance and efficiency compared to the general-purpose CPUs. Domain-specific languages, that is LLMs, etc., large language models, and all, are an example to how to improve the hardware-software interface that enables architecture innovations like DSA. Achieving significant gains through such approaches will require a vertically integrated design team that understands applications, domain-specific languages, compiler technology, computer architecture and organization, and CMOS, implementation technology. See, in this new era, the vertical integration has become more important, and teams that can examine and make complex trade-offs and optimizations will be of advantage. So we need LLMs, we need a domain-specific languages, we need a domain-specific architectures. Then we need to have a macro understanding of all these things to achieve the higher performance. Where exactly the problems are there in domain-specific languages, compiler technology, computer architecture and organization, and the circuit theory, and in your circuit theory. So this is basically the problem is. So we sorted out the problem for AI and ML. We have done because we have a powerful GPUs, etc. Then next what? Next, which is the most important thing, which hunting the people in the industry, is all about. So we have implementation bottlenecks. So this is the implementation bottlenecks. You use GPUs, use TPUs, use FPGAs. My laptop has got a FPGA. My laptop processor has got an FPGA inbuilt in it. It can dump its bit stream and it can run for a specific application. Possible. There are CPUs with FPGA technology today. And I have seen the one company which is making a microcontroller for industrial smart fans, for industrial fans, targeting industrial fans with FPGA inside, with CPLD inside. So it has a microcontroller, all the features of microcontroller plus CPLD. So you are going to get a microprocessors in the future in your laptops, in your mobile phones. In your mobile phones already you have FPGAs. In my mobile phone already we have FPGA. So the FPGAs are already a part and parcel of tabs, tablets, mobile phones, and computers. And it will be there. GPUs will be there in your CPU, in your laptop. TPUs will be there in your laptop. FPGAs will be there in your laptop along with the CPUs. Maybe I have an octa-core plus one FPGA plus one TPU plus one GPU, one security accelerator, maybe there in my computer. To connect all these things, to connect GPUs, connect TPUs, to connect all these things, and to connect all these things, and caches, threads, hardware threads, and all, I need a new protocol to connect all the computing elements. Is called as a CCIX, which got invented 3-4 years back, to make sure that in heterogeneous computing the connections are seamless. That is achieved through something called as a CCIX, that is a cache coherence interconnect accelerators for accelerators. So this is another thing which is very important thing today we are achieving is power over internet. You just connect a device to the internet, it gets powered automatically. Again, maybe at the camera level, maybe at the system level, we had these things from last 8 years, but at the device level, at the chip level, if you connect it to the internet, getting it powered on is something very, very new technology today. Then again, the next it comes to the open architecture. Okay, fine. We have apart from hardware accelerators, we have all these things in our CPUs. And again, what exactly this open architectures is all about? That maybe people might are talking about RISC-V, whatever the architecture it is. Now, if in your laptops, in your servers, you have Intel, in your mobile devices, in an electronic weighing machine in a shop, in your conductor ticketing machine, or else in a factory setup, in your mobile phone, you have an ARM processor. See, ARM is a emperor of digital world, and Intel architecture. That is very specifically the x86 architecture still rules the laptop and server markets. Means I'm not saying Intel x86 architecture. Intel along with AMD is ruling the server and laptop markets, and digital and embedded world ARM is ruling. So these are the two established architectures. Intel x86 and ARM different architectures is the established architectures, which are proprietary to the Intel and ARM respectively. Now the question is this: what is this open architecture? Why I need a processor? During my PhD 10 years back, one student came to me and said, "Sir, I want to design a new processor." Then I said, "Pagal ho gaya kya? Why you want to design a new processor? Use any one existing processor. You have already 2000 plus processors in the world already. Why you need to go and design a new processor? Well, where is the necessity?" The biggest problem is, okay, I will design the processor to get my grades better. I got an excellent grade, I got a grade and all. I published the paper, etc. Well, good. But if you have designed the processor, then how to use it? Are you giving me the compiler? If you are using a 8051, then there is a Keel compiler to use the 8051. If some BTech student or an MTech student design a microprocessor, then how to use it? Does he is going to give me the compiler, full tool chain for the complete software development? No. Then what to do with your processor? Throw it to the junk. This was the thought process. You have Intel, you have a ARM, already 2000 plus processors do exist. Then why you need to design a new processor? Then in the in University of California, Berkeley, a few people came up with a new idea of open architectures. Means called it as a RISC-V. It's a RISC processor. We'll keep the instruction set open source. Intel's its instruction set is proprietary. ARM's instruction set is proprietary. If somebody keeps the instruction set open source, does it a new thing? Are they doing any innovation? Is this anything beneficial to the world and the common man? Absolutely no. If somebody keeps the instruction set, and Intel and ARM are not keeping the instruction set open source, so that somebody will use them and implement as a processor, no, not possible. At the same time, if somebody gives the instruction set open source free of cost, and you use however you want, keeping it open and free, does it a new thing? No, absolutely no. Absolutely no. There is a Sun Microsystems Spark processor is there. There is some Sun Microsystems, there is a Leon processor is there, and there was a MIPS architecture by that time already, and few more architectures were already open source. Like very famous was Spark. Spark architecture from Sun Microsystems. We call it as an open Spark basically because its ISA is open. Then if that is the case, then why the RISC-V got a catch the imagination of many? Why the RISC-V catches the imagination of many? Already there, open architectures, open Spark is there. Open Spark is there from 25 years back, 1999 or 2000. They made the open Spark ISA free, and they call it as an open Spark. Anybody can use the open Spark. Then why the RISC-V catch the imagination? Why not open Spark? The question was, it is incremental. All our earlier architectures, so there is open Spark, Leon, Intel, ARM, everyone was an incremental architecture. But RISC-V is a modular architecture. Then what do you meaning by a modular architecture and an incremental architecture? Can anyone? Can anyone? Fine, let me put it. So the case is go back to the 1977. Your basic x86 architecture. How many instructions were there? Hardly 76, 77 instructions in your basic x86 in 1977. Hardly 70 plus instructions. Very precisely, I don't know. I don't remember. Now the question is. Now what is the process? Now currently I have a x86 architecture in my laptop. How many instructions are there for that? Somewhere around 2700 or 3000, nearing 3000. In 1977, I had an x86 architecture with hardly 70 plus instructions. In the 2024, I have x86 running on my laptop. I am presenting the PPT to you. It has got more than 2,700 instructions. In last 40 years or 45 years, Intel had it 2,700 instructions or 2,500 plus instructions to this architecture. x86 version 1, version 2, version 3, version 4. x86 architectures added around 2,500 plus instructions. Now the question comes, what is the harm in this? What is the worry here? What is the worry here? The worry is there. Worry is, the question is, how can you accommodate 2,700 instructions and keep up the performance? Lesser instructions, higher the performance. That's what the RISC architecture is all about. Less instructions, better the performance, right? That's what the RISC architecture is all about. But still, Intel don't want to go into the RISC way. It has to keep the all 77 instructions or 76 instructions which got implemented in 1977. All the instructions are even supported in my laptop today. In 2024, I have bought a laptop. I have an Intel processor in that. In 1977, what instructions were supported in basic x86, all those instructions are supported in 2024 processor also. Why this is required? Why this is required? Fundamentally, I'm a crazy guy. I want to install a 1992 version of Red Hat Linux on my laptop in 2024. I bought a brand new laptop 2 months back or 1 month back, and I installed 1992 version of the Red Hat Linux on it. It got installed. Problem is, I am crazy. Even though my hardware is 2024, I want to run an operating system of 1992. That's the reason the Intel keeps all the instructions supporting. It won't delete any instructions. It keeps add to the existing instructions. Because we don't know which crazy customer want to install an operating system of 2002 or 2004 or 1992. Which crazy customer wants to install an operating system of 1997 in 2004 or 2024? That's the reason Intel or ARM will keep on adding the instructions that don't delete the previous instructions. This is basically a problem for their performance improvement because they don't have a choice of deleting the old instructions. So that's why we call it as an incremental architectures. We keep adding the instructions to the existing design and we'll make a new processor. We don't delete the previous instructions. But RISC-V, you don't have that problem. It defines basically a 47 instructions, which everybody implemented. If you want any other instructions, it is for you. It is only for you, not for others. Not for others. If you are implementing, it is your problem. But it is suggested that operating systems or any RISC-V system software, basically operating systems, compilers, or tool chain, whatever the system software, what we call it as system software, all the system software should use only those 47 instructions. Because we don't know what instruction, what guy will use. Which instruction who will design, we don't know. But if you are calling it as a RISC-V processor or RISC-V processor, the basic 47 instructions defined by the RISC-V consortium at University of California at Berkeley must be implemented. Those 47 instructions are freezed. Neither they will decrement it nor they will increase it. They will keep those 47 instructions freezed permanently, eternally. So if you are designing an operating system, use those only 47 instructions. For example, somebody who buys a RISC-V based processor in 2042 or 2048 and want to install an operating system of 2027 or 2024, still he can install it because the operating systems will use only those 47 instructions. That's the reason why the RISC-V is modular. Why it got a imagination? Why it got a it solved the problem of system software. Yeah. Yes. Yes, please. Yeah. So the RISC-V catches the imagination of the world just because it caught the imagination of the modularity. It caught the imagination of a modularity. So you can design an operating system now, and you can install the same operating system in 2082 on the RISC-V processor without any problem. And the performance is damn good because it's not incremental architecture. No overload of instructions, less like a Intel or ARM. So this is what why the RISC-V become boom. Why the most of the architectures are moving towards RISC-V. Maybe Intel may die, ARM may die in next 20 years, but RISC-V remains. So if you have not started with RISC-V, start it. In PS University, we teach computer organization with RISC-V. We neither teach Intel nor teach ARM. We go with an RISC-V now. So this is all about this one, the Intel, the architectures, why we need heterogeneity, why the mapping of algorithms become more important after 2014. Before 2014, even I discouraged the work related to that because it does not necessitate a industrial research. After 2015, even industry is hunting people with that skill, mapping algorithms to architectures. So this is what exactly the required is. So now let's come to the basics of, because if you don't cover anything basics with mapping algorithms, I don't think it will do the justice. Then let's look at the only three aspects I will tell, the three components of this FR field, this mapping algorithms to architecture. See the mapping algorithms to architecture. Mapping algorithms to architecture. The only three things. One, you know FR filter. Y of n is equal to A of x of n plus B of x of n minus 1 plus C of x minus 2. So this is the FR, the basic architecture. How can you map this one to the hardware? Simple. Get the multipliers here, get the adders accordingly. In the place of a delay element, you just add a flip-flop. Done. Have a flip-flop here, have a flip-flop here, and ABC are the weights, and get it multiplied, and you got a Y of n. So just its job done. The critical path is two multipliers, one multiplier here, and two adders. This forms a critical path. There ends the story. There ends the story. This is a very basic, fundamental FR filter architecture. Now let's see something else now. Why you want to implement this way? And if you implement this way, as the conventional way, what we have discussed here, you have a one multiplier on the critical path, and you have a two adders in the critical path. The critical path will become a multiplier plus two adders. But can I implement in this way, whatever I have shown here? This is a normal generic way of implementing it, FR filter. Can I implement it like this? CBA, just reverse the order, ABC instead of ABC, make CBA, then again make this architecture. If you make this architecture, here one multiplier will come, one adder will come. The critical path will become one multiplier and one adder instead of one multipliers and two adders. In this case, it is two multipliers and it becomes one multiplier and two adders in this case. In this case, the same FR filter is one multiplier and one adder. But still, most of the engineers prefer this architecture than this, even though critical path is very less here. Why? You see this FR filter architecture for same implementing A of x of n plus B of x minus 1 plus C of x minus 2. So for the same thing can be implemented in this way. in the whatever is shown in the blue color, ABC, and critical path will be one multiplier and two adders. The same thing can be done here with one multiplier and one adder, but still the engineers prefer this. Why? The simple reason is fan out. Here you need to drive only one multiplier, but here you have to drive the three multipliers. Fan out more, the combinational fan out is high, your capacitance will go high, and it's a unimaginable delays will be there in this architecture than this architecture. The fan out will be 10 times greater than the critical path what it comes here. So here the critical path is high, but fan out is less. Here the fan out is very high and the critical path is very less. But fan out is more dangerous, so I will go with this architecture. That's the fundamental reason. Okay, this is one part. The next is this one. Why we need odd-even implementation of an FR filter? The question is, the fundamental problem is, why we will go for a C? I will break the incoming signal into odd and even. 0, 2, 4, 6, 1, 3, 5, 7. I will break them into the two pieces. One is x of 2n and another one is x of 2n minus 1. Then I will give it to the flip-flops with the 2t clock, not 1t clock. So x of a k is coming inside with the t clock. X of k is coming inside with the t clock. I will break them into the two streams. Then I will run the FR filter. Just see, this is an one FR filter. One FR filter in blue color, another one in purple color. So this becomes one stream of y of 2 of n, and this forms a y of 2n minus 1. Then I will merge them into the t clock domain. See, before this yellow line, yellow line, the clock domain is t, and after this yellow line, the clock domain is t. But my FR filter implementation happens in 2t. So here the t clock is 2t. Before breaking into the odd and even, it was t. After merging, it will become t. Only this FR filter application, FR filter operation will happen in 2 times of the clock period. So here the frequency is 100 megahertz. Here it is 50 megahertz. Here if it is 10 megahertz, here it will be 5 megahertz. Then what is the main application? When we will go for this architecture? Any idea? When we will go for this architecture? Any idea? Simple. The customer is asking to deliver a FR filter at T frequency. But unfortunately, I don't have a multipliers and adders which works at T frequency. I have multipliers and adders which works at a lesser frequency. I have adders and multipliers, but not matching the T frequency or 50 megahertz or something like that. But my adders and multipliers will work at 25 megahertz. If that is the case, then I will make it as like this. I will break it. I will do a FR filter and merge it and give it to the Y of n. Customer feels that it's a completely working at 50 megahertz, but eventually it works at 25 megahertz. I achieve my target. I satisfy my customer to 50 megahertz, even though I have adders and multipliers with 25 megahertz by looking into the odd even FR filter. So these are the few glimpses, because I don't want to get into the deep mathematics of mapping algorithms to architectures, which will be boring, which does not address all the audience, because maybe one or two may be working in that particular area. I can take an example of image processing, or I can take an example of FFT, or I can take an example of AI/ML itself. But the question is, I don't know how many in the audience are working in mapping the algorithms architectures. But if I say the nuances of mapping algorithms to architecture, why this architecture becomes more important for FR, why not this? Even though critical path is less, the biggest problem is the fan out here. The problem is fan out here. The next, in this case, if you don't have a combinational blocks, especially the adders and multipliers to the given frequency or the required frequency, what can be done? If it is a FR filter, you can do this and make it logically, technically. You do the architectures, you can parallelize something and get the then do the work out the design for the higher frequencies and all. This is a one classical example towards that. Okay, now this is after this two classical examples. I don't want to get into the more this one because I don't know the audience. The question is now, this is one architecture what I'm showing. One architecture of very recent or not recent, maybe 1.5 year old microprocessor or microcontroller from NXP. I didn't see this architecture in 2005, 2006 when I was working in Wipro Biomed or Freescale Semiconductors or GT Enterprises. So I had only few things like one processor, serial communication, and timers and ADCs. That's all. One processor here of multi-processors, one processor, then the serial communication module, then some timers and ADCs. This makes my microcontroller. But today, what extra is there? You have a security engines. Hardware security engine is there. This is not any mobile phone or rocket chip, nothing like that. This is a chip which is meant for conductor ticketing machine, a weighing machine in a retail shop, a card scratching machine in a mall, or 1 rupee coin phone booth, anything like this. This processor is meant for this one because security is important today. And again, there is a network accelerators. There is a Ethernet acceleration. You can see there is a complete Ethernet acceleration happening here. Whatever the software stack of 7 layers, OSI layers, right? 3 layers, you can get it here. You have a OSI layer, 7 layers, right? Network theory, means computer network theory. All 7 layers are not in software today. At least the basic hardware layer to the 3 layers, 4 layers come in the hardware itself, inside the microcontroller itself. Map them. Use QUIC. Use network interface cards. Do the hardware architectures for network interface cards. Do the hardware interfaces for OSI layers. Do the hardware architectures for CAN-FD, FlexRay, CAN-XL, EtherCAT, all these things. You do the hardware architectures. Nobody's trying that one in academia. Very less people are trying mapping algorithms to architectures in network acceleration or Ethernet networks. Then it's not only the signal processing required, it's also a communications required. Go to the websites of the Broadcom and BCM Communications and look at their architectures. Look at their offerings, look at their chips. What they are doing they are completely building all 7 layers in the hardware. All 7 layers in the hardware, all 5 layers in the hardware. Even part of an application layer, they build it in the hardware. This is where exactly we need to look into in the future. If you want to do PhD, implement a EtherCAT, implement a CAN-XL, implement a security engine, especially not the conventional AES, not the conventional hash algorithm. Go for a post-quantum cryptos. My students, most of them are working in PQC, post-quantum cryptography, and they are challenged every day, almost every week. Every week we are getting a new papers in early access of IEEE transactions on VLSI on PQC algorithms like Kyber, the lithium, etc. Just let's come back to this architecture now. This is a simple microcontroller architecture meant for the simplest applications like weighing machine in a retail shop, a conductor ticketing machine, 1 rupee coin phone booth. So this is you have got how many cores here? 3 cores in 3 core dual lockstep, and there is a 3 cores plus 2 cores plus 2 cores in a cluster lockstep. What you can ask a lockstep? Lockstep is a one feature required for the functional safety. A functional safety in the automotive engineering. So let's keep that one aside. What is a lockstep and all? Please Google it if you don't know. But here 3 cores plus here 4 cores. 3 plus 4, 7 cores. But these 3 cores in tandem to make it as a dual core lockstep. And these 2 cores, these 2 dual cores are in a tandem to make it as a cluster lockstep. So so many processors, basically the 7 processors with accelerators for network, accelerators for Ethernet, accelerators for security. It has nothing to do with signal processing, nothing to do with image processing, nothing to do with AI, ML, anything like that. Here there is nothing to do with AI, ML, nothing to do with your DSP, nothing to do with image processing, anything like that. Still, you can build an hardware for security, build an hardware and do PhD in network accelerators, do in Ethernet OS layers acceleration, build a efficient network interface cards. Possible. That is what I am asking. What next of AI? What is coming out of AI? What next of AI? Based on this explanation, I'm looking basically focusing on what next. It's a security. Yes. AI bet is over. Yes, it's over almost. No low hanging fruits, all high hanging fruits. The next is security. Where exactly the security? It's a post quantum cryptography, not the conventional cryptography. If you are still working in conventional cryptography, dump it. Start reading post quantum cryptos. If you are a communication engineer, start learning quantum key distribution, quantum communication. It's not a great rocket science. It has no applied physics. It's just another communication subject. That's all. Then security in the open architectures like RISC-V at various dimensions is all the things which is coming on your way, where you can do your VLSI research, chip design research. Functional safety. Already I said lockstep processing for functional safety. You need to design a novel architectures for addressing the radiation effects at macro level, at system level. Lockstep processing, you Google it in the interest of time. It's something like that. Lockstep processing means I have a two processors running the same program with 5 cycles delay, 2 cycles delay, 3 cycles delay, etc. 3 cycles delay, etc. So this is called as a lockstep processing. So it is required in the functional safety of automotive cars, buses, etc. Then what next? What and all are there in? Apart from DSP is over, security is over, AI is over, network is over, Ethernet is over. Then what next? In healthcare, you can look at the DNA sequencing architectures. PCR testing, RT-PCR testing, COVID-19 testing. You can design a SOC for COVID-19 testing. Less PhDs are there. Less work is done. Low-hanging fruits are there. Go and do PhD. Go and do research in these areas. Get your publications. DNA sequencing and cognitive technologies. A lot of cognitive things are there, which I don't want to get into. Then exactly, now the electric vehicle is a big thing. What exactly we need? We need a system on chips or battery management systems. We need a processor for EV chassis, motor control, motion control, etc. And fire safety, functional safety and all. We need a system on chips for EV charging infrastructures. That none of these three architectures do exist today. Go ahead, do research and get publications, get patents, get jobs in the industry. In the healthcare, in EV, yes, a lot of functional safety, security, these are the areas where you need to look into. The biggest thing is digital twins. There's a digital twin is another vast area which includes AI ML algorithms, which includes all the physics, applied physics, all these things. We need a very, very strong computing architectures to implement a digital twins holistically. It's completely unexplored area, which is a very, very raw open field. If you sow anything, the crop is guaranteed because land is virgin. Digital twins. Then again, I come to the defense and crypto. Why? Because the FDP says something connected to the defense. Then if you want to look into the DRDO labs or any defense applications, what exactly they're looking for? They're looking for the newer microarchitectural attacks like Spectre and Meltdown. I think most of you might know about the Spectre and Meltdown. These are the two great side channel attacks which can hack your computer from anywhere in the world if you are connected to the internet. Spectre and Meltdown are the two dangerous attacks anybody can mount if he has a technical skill, sitting in Antarctica and hack your hard disk. Possible. The only solution to prevent this attack is redesign your complete microprocessor against power leakages, side channel leakages against Spectre and Meltdown. Either your Intel processor or your ARM processor is not equipped to defend against Spectre and Meltdown. Then what to do? Take a RISC-V, design and RISC-V processor which will prevent spec-driven meltdown. Redesign your complete instruction set, 47 instruction set or any other complete hardware to prevent meltdown on spectrum. That's it. Then what is other physical and clonable functions which is widely described? Use physical and clonable functions for chip security, documentation, and mask for production. And side channel attacks and mixed signal circuits, blockchain for defense applications, access control and trust management. Again, hardware for this. These are all exactly the where VLSI signal processing will come into the help. The mapping algorithms to architectures is really required in designing the new, preventing the new microarchitectural attacks like Spectre and meltdown. If you design a FPGA-based microprocessor which prevents Spectre and meltdown, and again design a mixed signal circuits which don't leak power at all, so nobody can mount attacks on them. And the blockchain acceleration, which is the blockchain is basically runs on software, but some amount of things must be there in the hardware to ensure that security, because the security is more when it comes from the hardware. The root of trust is more strong in the hardware than the software. So the blockchain in software, yes, it is well established, but bring something to the hardware to make it more safe, especially for the defense applications. Then what are the algos you can make? Find out a new encryption algorithms like ASCON or Rudra or THFE, anything like that for military IoTs. Hack-proof cryptography with honey encryption. Find out what is honey encryption. Honey encryption means you are giving some data, and the hacker will assume that it's hacked, but it will, at the end of the day, it will give the wrong data. It will honey trap the hacker, and it will get its details. Don't give your details. That is what exactly the honey encryption is all about. If somebody tries to hack you, instead you will get hacked. That is called as honey encryption. Then node encryption for communication security. These are very common things, but encryption for military IoT. Find out a new algorithm like ASCON, Rudra, THFE, etc., and prove that it works for military. Then honey encryption, FPGA implementation of honey encryption, we don't have any papers. Hardly 1 or 2 papers may be there on FPGA implementation of honey encryption. Try something. Then again, cryptanalysis, bio-inspired crypto algorithms, homomorphic algorithms, post-quantum side channel. These are all the algorithms which make sense. So these are the references, what I used. And thank you. Any questions I can take up? Yeah.
Yes, sir. It's a wonderful session, sir. There are a few questions in the chat box, sir. Can I read out, sir?
Please.
Sir, does Moore's still work for circuit design?
No.
That is one question, sir. And
see, fundamentally, if you are working with the FinFETs, right? If you are working with the FinFETs, multi-gate FETs at 40 nanometer and all, if you are designing a standard cell libraries, it's no more a CMOS. My CMOS inverter characteristics does not fit my FinFETs, double gate and all. And again, we don't bother about, in the universities, we don't bother about bringing the FinFETs to the UG curriculum, and not required also, because most of the designs in the digital happens at the gate level. And if whether it is a CMOS library or whether it's a FinFET library, it does not make a difference. So that's the reason why we don't bring the FinFETs into the UG curriculum. So my synthesis happens at gate level. I'm not worried. So the Moore's law holds true only largely up to 45 nanometer or 65 nanometer, not further. Frankly speaking, some honest scientists say that Moore's law died in 2003, but for marketing reasons, it was kept alive next 10-15 years. Yeah. I hope I answered your question.
Yes, sir. Yes, sir. So next, one more question, sir. There is a term SysMoore. Can you throw some light on it? The question was SysMoore. SysMoore.
In my presentation?
I think the Damayanti Singh asked this question. SysMore. SYSMOOR.
Is it spell out SYSMO?
SYSMOORE. Damayanti Singh, ma'am, if you are online, you can ask, can interact with resource person.
I think you are seeing my screen, right, sir?
Hello,
Yes, sir.
good evening, sir. This is Damayanti Singh.
Yeah, please,
I have
madam.
a question. Yeah, good evening, sir. First of all, it was a very nice presentation, so thank you so much for this.
Thank you.
Actually, sir, recently I have attended some FDP, and there was a point key Moore's law. It is still working in the industry level, and now this Moore it has been replaced by term SysMoore.
It
So
means,
the
to the best of my knowledge, it's all marketing gimmick, but Moore's law died long back. Moore's law's not died, it stopped working long back. I don't know what is SysMore is. Yeah, sorry. Yeah.
Oh, okay.
Yeah.
And also, sir, actually, one more question, sir. In industry, there is a currently in the industry the work is going on at 2 nanometer. And also, it is possible that they will fabricate some device which will work at 1 nanometer as well.
Well,
But is it possible that a device can be fabricated at below nanometer scale?
yeah. See, if somebody says 7 nanometer, if somebody says 5 nanometer,
Yeah.
it's not 5 nanometer. In physical terms, it's not 5 nanometer. If somebody says 3 nanometer, in physical terms, it's not 3 nanometer. It's somewhat 20 nanometers or 18 nanometers, somewhere in that line. But its performance matches with 3 nanometer or 7 nanometer. The physically fabricating a chip below 14 nanometer is quite difficult.
Yeah.
And 7 nanometer and 5 nanometer, it's a physically quite not possible. It matches the performance of a 5 nanometer technically.
Okay.
And below nanometer scale, we don't know what happens. At some point of time, the people said that graphene will replace the graphene material will replace this silicon and all. We are using silicon today to fabricate chips for bringing up the MOSFETs and all. Something like graphene can go below nanometers and all. So a lot of materials are suggested, but I don't know what exactly it is and what industry is thinking in that direction to replace the silicon with for below nanometer technologies.
Thank you so much, sir.
Thank you very much.
Sir, one more question, sir. Dr.
Please.
T. Selving Ratnaraj sir asked this question. When the cache is working fast, due to what happened? Sir, when the cache is working fast, due to what happened? Think.
Yeah, the caches came into existence with the Super H architecture somewhere in 1997, 1998. Especially the analog devices introduced the caches very first time somewhere in the late 90s for the Super H architectures, especially the DSPs. Gradually the Intel adopted it, and gradually everyone adopted the cache architectures at the different levels, L1, L2, L3, etc. The question is I cannot have a caches at all the places wherever required. And again, every cache needs an address management and a DDR controller or memory controller. So there is always a latency in the cache. The processor works at an higher frequency and the memory and caches at a lower frequency to match some physical constraints like setup time, etc., hold time, clock to queue delays, etc. and all. The question is, yes, caches are good, but apart from one point, having a cache at every place is not possible, and making the caches work at a higher rate is quite not possible because of the implementation issues. And the caches cannot be faster than the processor. There are some cases double data rate and all can be achieved near to processor, but there is the implementation bottlenecks. in different dimensions. One is a setup and hold and timing failures, functional failures, thermal runways, reliability issues, yield issues, testing complexity. Yes, n number of things, n number of engineering problems comes when you increase the caches than the existing L1s, L2s, and L3s.
Yeah, sir. So one more question. Sir, how do we use FPGA in electric vehicles, EV technologies? How do we
Yeah,
use
great question. Good question.
FPGA in EV? Yes.
Yeah, go and implement a OCPP security architecture in FPGA. Electric vehicle charging infrastructure needs a OCPP protocol to connect the grid to the vehicle and all. The OCPP protocol is a digital protocol, and it needs a security. Go and implement a OCPP security in FPGA. It's a one low-hanging fruit. Easily, I can say, without any much thinking. And again, electric vehicle needs a motion control, motor control, and functional safety issues are there. Lockstep processing is required in electric vehicle. So make your FPGA based functional safety engine, FPGA based security engine, FPGA based charging say secure charger for your electric vehicle. Why not? There are a lot of low hanging fruits.
Yes, a good insight, sir.
Yeah.
So, next one, is there any scope for research on CNT FETs?
Sir, sorry, I'm not from device side.
Okay, sir. Giving insight into side channel attacks.
Yeah. Side channel attacks is basically it was done at okay. Yeah, this is one side channel rough slide I have. See, in the side channel, basically when it all started is Paul Cocker side channel attack in 1998. How exactly my computer science counterparts will attack the cipher? Means they have a cipher. Let's take example in cipher. Put a data, put a key, and get the encrypted data here. I don't know. Key is a secret. I don't know what is the key. Just I will keep pumping the data. Data set 1, I will get the encrypted data set 1. I will send the data set 2, I will get the encrypted data set 2. Like that, I will collect different data sets, completely different data sets. Let's take 1,000 data sets I collected. Data set 1 to data set 1,000. Then I have encrypted data 1 to encrypted data 1,000. Encrypted data 1,000. So if with these two I have a data and this corresponding encrypted data, I will use my statistical techniques and break the key. So possible. It is easily possible. That is how my computer science friends will break the cipher. So you have a data, you have an encrypted data, 1,000 samples, you collect it and break it. The question is, in this way, if this is the process, I can break all the ciphers which was designed in the past, which will be working now, and which will be designed in the future. Whatever the ciphers you design in the future, I will break all the ciphers using this technique. It is possible. The problem is here, I don't allow the attacker to collect 1,000 samples, 1,000 data sets and 1,000 encrypted data sets. I won't allow the attacker to collect 1,000 samples at all. Every 5 encryptions or every 10 encryptions or every 3 encryptions, I will change the key.
Thank you, sir.
On every 20 encryptions, I will change the key.
Thank you, sir, for your valuable clarification.
Yeah, if you have a key changing every frequently, collecting 1,000 encryptions is useless. Then I want to collect only 10 encryptions and break the key. Then what I will do is, I will just collect 10 encryptions, but also I will collect the power consumption for each encryption here. So I'm getting one more data. Apart from the data and the encrypted data, I am also collecting For data 1 and encrypted data 1, what is the power consumption? For data 2 and encrypted data 2 conversion in the cipher as how much power is consumed. I will have also P1 to P10. I have a 10 data sets, 10 encrypted data sets, 10 power data, power consumption data, especially the dynamic power data or switching power data. With these three components, I can break the key with 10 encryptions. I don't want 1,000 encryptions. My Google Chrome, which I am using now, will encrypt, will change the key very often, will change the key for every 6 data transfers. With 6 data transfers are enough to conduct the meltdown attack on my laptop. So this is what exactly the power is side channel attacks. Side channel attacks means we don't want 1,000 samples to get collected and break the cipher. With 10 encryptions, and then for these 10 and corresponding encryptions, how much power is consumed. If the data is available, I can break the key using the techniques called simple power analysis, differential power analysis, and correlation power analysis. And also, it's not limited to the power. It can be a timing attack. It can be a fault attack. A fault attack means creating a 1/0 like situation in the software, or creating a disturbances in the clock, creating the disturbances in the power supply, creating the disturbance in the resets is also a fault attack. And using the DFT structures, VLSI testing structures to create attack, using the, along with power, using the electromagnetics and laser based side channel attacks are also possible. But power attacks is saturated, timing attacks is already saturated, fault attacks, or a lot of thesis is there. Test attack is already 20 years old, but multi-level attacks you can try. Means I will use timing, test, and power. I will do the attack. The multi-level attacks, yes, possible. I hope I covered the basics of side channel attacks.
Thank you, sir. Thank you, sir. I think you've given a detailed explanation about that side channel attacks.
Thank you. Thank you.
So there are 2 more questions, sir.
Please.
If you don't mind. What is meant by IC performance is of 3 nanometers? What is meant by IC performance? What is meant by IC performance is of 3 nanometers? I think this question is covered in previous discussion. Like it is related to performance.
See the performance. See, for example, if you are using a 90 nanometer technology, what is the maximum operating frequency of 90 nanometers? Can I use 10 gigahertz clock? No, 800 megahertz is the limitation. Worst of the worst case, I can use 1 GB, means 1 gigahertz as a clock for 90 nanometer. For 130 nanometer, you cannot go above 600 megahertz or 610 megahertz or something like that for 130 nanometer. For 180 nanometer, you cannot go above 350 megahertz. I'm talking about the digital implementations or processor implementations. I cannot run 180 nanometer processor at 500 megahertz, not possible. Quite not possible. Because the channel length does not support it. 90 nanometers can go up to 1 gigahertz or 1.2 gigahertz very rarely. At the same time, if you come down to the 65 nanometer, it can reach up to 1.5 gig. If you go below 45 nanometer and all, it keeps increasing. It can go up to 5 gigahertz and all. So this is what exactly I don't know about below 28 nanometer. I have no idea because it's no more a CMOS. I hope I answered your question.
Yes, sir.
Yeah.
So can FinFETs can handle high currents as BiCMOS?
No. To the best of my knowledge, no. That is the reason why BiCMOS is required. Where you need a current drive, you need a BiCMOS. Where there is no current drive required, we don't want a BJTs at all.
Yes, sir. Yes, sir.
That's the reason why even today the power amplifiers required for my speakers are designed using BJTs. That's the reason, right? Even my laptop speakers or even any of my speakers are large meeting speakers and all based on power amplifiers, based on BJTs, because
Yes, sir. Yes, sir.
BJTs can get the more current.
Correct, sir.
Yeah.
Devi Pradeep, sir.
Yeah.
Devi Pradeep, sir. Okay, can you ask question?
Yeah, yes, sir.
Yeah,
Is
please.
gallium arsenide devices are existing in the contest related to the high-speed applications, sir?
Sir, gallium arsenide is a different application. We have a lot of other applications, especially the discrete components, right?
Oh, okay, sir.
The
Okay.
discrete components like power MOSFETs, this and again the thyristors, the high energy transistors, and all needs a gallium arsenide. The especially the lasers, the laser optical electronics uses a gallium arsenide widely, and I don't think the chip designers need a gallium arsenide. Only the discrete components meant for very specific applications in very specific areas uses a gallium arsenide.
Okay. Okay. Thanks.
Yes.
Sir, I think questions are over, sir.
Thank you, sir. Your valuable time you spent with us. Actually, we gathered a lot of things from you. We also
Thank
tried
you
to
very much, sir.
implement.
Thanks for giving me an opportunity to share whatever I have with you, all of you people.
I am one
It's
of
a
the
pleasure
participants,
coming
sir.
back to the GMRIT again and again, and it's a great place to visit. At maybe sometime physically I come there for GMRIT also. Maybe you have given me an opportunity from
Sir,
so many years
if you
to.
don't mind, sir, if you don't mind, you can share your contact number as well as email ID.
Yeah.
So if you have further
Yeah.
clarification, we can utilize in future, sir.
Yeah, sir. This is my email ID. I hope it is visible.
Yeah. Yes. Just wait a minute, sir. We will
Just
note
I
it.
will make a.
Yeah. Just
My mobile. Yeah, I think it's enough.
Yeah.
Yeah.
Thank you, sir. Thank you for your valuable presentation, sir. And you have bad your time.
Thank you, madam. Thank you very much for giving me an opportunity. It's
Thank you
always
so
a
much.
pleasure to come back to GMRIT. Maybe.
Yes, sir. Please, sir.
Yeah.
We always welcome you, sir.
Thank you very much, madam. Thank you.
Now, so just for a concluding remarks, I request Dr. B. Anil Kumar, Assistant Professor of EC Department, to give his concluding remarks of the session 2.
Yeah, good evening, all. Am I audible, madam?
Yes, sir.
Yeah, audible.
Good evening, all. I am Dr. Anil Kumar B, faculty in the Department of EC GMRIT. So, on behalf of Department of EC and participants, I extend my heartfelt gratitude to Dr. Sudhindra Kumar sir for delivering an enlightening session on mapping algorithms to architectures. What next after AI architecture as a part of 6-day ATAL online FDP. Your session provided comprehensive journey covering basics of Moore's law, Denner's law, and other fundamental principles of related to the hardware architecture, domain-specific languages, and RISC-V architecture. It then delved into advanced topics like mapping algorithms and exploring what lies ahead beyond AI architectures, including security and functional safety. And you have given wonderful examples like digital twins, medical applications, and defense and cryptography related applications. And the highlighted thing is the finally have given a very good research directions to the people who are doing in research in VLSI domain. And this structured approach and the depth of insights you shared with greatly enriched the participants' understanding and sparked their curiosity to explore further. Thank you once again for your valuable time, energy, and contributions. We hope we have privilege of hosting you again in future for more such impactful sessions. Thank you very much, sir.
Thank you very much, sir. Thank you very much. Thanks for giving me an opportunity. Thank you, madam.
Thank you, sir. Thank you, sir.
Thank you very much, madam. Yeah.
Thank you, sir. So now I request all the participants, we have given the day one feedback link to the chat box as well as in the WhatsApp group. So please submit your feedback within 30 minutes or half an hour.
Ma'am, when is the tomorrow session, ma'am? As usual time.
Tomorrow we'll start by 6, sir. 6 to
Okay,
7:30 will be session 3 and 7:30 to 9 will be session 4, sir.
Okay, thank you.
Okay, sir. So thanks to all the participants for your patience listening. So thank you once again.